Hello there and welcome to Just About Earth, where late nights settle into gentle curiosity and science unfolds slowly enough to rest beside. Tonight we're wandering into one of the strangest blank spots in our planet's memory, a period tucked deep in the prehistoric timeline where something significant seems to have happened, yet nearly all evidence of it has disappeared. It's a gap scientists still argue over, a quiet stretch of geological history that behaves less like a chapter in Earth's story, and more like a missing page torn out long before we arrive to read it. Before we ease into that puzzle, I'd love to know where you're listening from tonight. Maybe you're winding down after a long day, or settling into bed with the lights lowered and your room calm around you. Whatever the hour in your corner of the world, I'm glad you're here keeping me company, while we explore a time so distant that even the rocks struggle to remember it. And if you find this slow drift into Earth's deeper past soothing, or simply a peaceful way to let the day fade, it would mean a great deal if you gave the video a like or maybe subscribed. It helps this quiet little corner reach others who might enjoy resting alongside old mysteries too. There's something inviting about easing into the unknown, especially when the unknown isn't dramatic or loud, but quietly puzzling. The moment you hear about a prehistoric time gap, your imagination might leap to sudden catastrophes or long-forgotten creatures, but the truth tucked beneath layers of sediment and missing fossils is much stranger than that. It's not a story about what we know happened. It's a story about what the Earth refuses to tell us. Our planet has a long habit of preserving some things beautifully, while letting others vanish without explanation. And this particular gap stands out because it behaves as though an entire stretch of history once existed and then slipped away without leaving more than a few faint hints behind. It's like opening a book that has been weathered by centuries and noticing that the ink has faded only on certain pages, leaving you with more questions than answers. To settle into this mystery, imagine holding a timeline of Earth, not just the familiar moments of dinosaurs or early mammals, but the enormous expanse stretching billions of years before all of that. Most of that timeline is filled with fragments of clues, fossils, chemical signatures, ancient sediments, and the occasional microscopic imprint left behind by early life forms. For the most part, scientists can arrange these fragments into a reasonably coherent picture, one layer sitting atop another in a sequence shaped by pressure, erosion, and unimaginable stretches of time. But then, as that timeline unrolls, you reach a strange thinning. The traces get sparse, fossil beds grow quiet, the sedimentary layers look disturbed or incomplete. It's as if something moved through history with a broom, sweeping entire sections into obscurity. And no one knows precisely why. These kinds of absences might sound ordinary, after all the Earth is constantly remaking itself. But the prehistoric time gap we're easing into isn't just a smudge or a missing specimen here or there. It's large, consistent, and globally visible. It stretches across multiple continents, appears in formations that should hold steady records, and interrupts the natural flow scientists expect to see when reading geological layers. You might think of it like walking along a beach and noticing that the footprints, shells, and driftwood suddenly vanish for a long stretch of sand before reappearing again. It's not that nothing existed there. It's that everything seems to have been erased. This makes the gap more than just an intriguing oddity. It becomes a kind of silent question. What happened during those missing ages? Did life retreat into hidden places where it left no visible marks? Did environmental conditions transform the planet in ways that prevented fossils from forming? Or did geological processes rearrange the layers long after they settled, scrambling the record so thoroughly that piecing it back together feels like trying to reconstruct a puzzle without corner pieces? Each possibility has its supporters, yet none fully solve the puzzle, and that makes this mystery perfect for a slow night's wandering. Not a frantic chase for answers, but a calm look at how much of Earth's earliest past has quietly slipped beyond our reach. To understand why this gap matters, consider how scientists usually build their picture of ancient life. Fossils capture shapes that once moved across ancient seas and soils. Chemical clues hint at what kind of atmosphere surrounded them. Rock formations tell us whether the world was warm, frozen, shallow, deep, oxygen-rich, or starved. But during this time gap, many of those tools stop working or become unreliable. It's as if someone dimmed the lights just when the story was reaching an important turning point. And so, researchers must lean in, squint, and interpret faint cues left behind in sediments that have been worn thin or reworked by forces long gone. But even in this dimness there are whispers. A few layers still contain odd remnants. Strange isotopic shifts that hint at global changes. Gaps in evolutionary lineages that suggest something interrupted or slowed life's progress. Signs that the environment might have shifted in ways the planet hadn't yet experienced. None of these hints are definitive, but together they offer a faint outline of something unusual happening. Something significant enough that the planet's memory blurred around it. Part of what makes this blank space so compelling is how it challenges our sense of stability. We're used to imagining Earth as a giant archive where the past compacts itself neatly into layers waiting for us to study. But nature doesn't follow filing systems. Each layer is vulnerable to erosion, heat, pressure, or shifting crust. Floods can sweep away entire regions. Earthquakes can fold rocks like cloth. Volcanic activity can bury landscapes under fire or melt them into new shapes. Over hundreds of millions of years, these processes don't merely cover the past, they rewrite it. And so this time gap may be less a sign of disappearance and more a sign of the planet's restless nature. Still, the question lingers because the gap aligns with important transitions. Life was changing around this period. Early organisms were diversifying, oxygen levels were fluctuating, and global climates were shifting in ways that could influence evolution and extinction. The scarcity of clues doesn't simply frustrate researchers, it obscures the explanation for how the world moved from one era to the next. Was there an environmental bottleneck? Did some global event push species to adapt rapidly, leaving little behind? Or was the world gradually becoming more complex, and the gap reflects only our inability to detect fragile early changes that didn't fossilize well? Each interpretation requires patience, careful analysis, and a willingness to accept that some answers may never fully come to light. And that leads us back to the soothing nature of the unknown. There's something strangely calming about accepting that the Earth holds secrets too old and delicate for us to reconstruct completely. This kind of mystery doesn't demand urgency. It invites curiosity instead of certainty, letting us step gently into deep time and consider how enormous the planet's story truly is. Much of what happened during those early ages unfolded in silence, without witnesses, without footprints, without the kind of durable remains that survive billions of years. The creatures that lived then, if they lived at all in significant numbers, moved through oceans or microbial mats that left subtle marks easily washed away. Entire ecosystems could bloom and fade without leaving so much as a single clear fossil for us to find. Yet the absence itself becomes part of the story. It reminds us that the Earth we know today, vibrant and full of memory, was once a place where the record kept slipping away as quickly as it formed. Life didn't always leave sturdy bones or shells. Many early organisms were soft-bodied, tiny, and poorly suited for fossilization. Even small shifts in chemistry could dissolve what little structure they had. And so the gap may reflect a time when the world was teeming with delicate life that simply didn't have the means to preserve itself. But even that explanation doesn't cover the full expanse of the missing interval. Some sedimentary layers that should show continuous deposition instead show signs of interruptions. Surfaces that appear as though they were exposed for long periods before new sediments covered them. Indicators of erosion where there should have been accumulation. These details hint that environmental processes were sweeping clean entire regions of Earth's surface. Maybe the seas retreated, exposing areas that later washed away. Maybe tectonic forces lifted parts of the crust high enough to erode dramatically before settling again. Whatever the mechanism, it carved out gaps that stretch far longer than scientists would expect from ordinary processes. And this is where the puzzle deepens, because these disruptions don't appear in just one region. They show up across many continents, often at similar times. That suggests something global may have been happening. Not necessarily catastrophic, but significant enough to leave a signature in the geological record while erasing much of what lived within that interval. Some researchers propose climate instability, with dramatic swings in temperature affecting sea levels and erosion. Others suggest shifts in ocean chemistry, possibly linked to changes in microbial activity, which could alter the kinds of sediments that form. And a few speculate that unknown events, subtle, long-lasting and not easily captured in the rock record, reshaped conditions planet-wide. These ideas remain in conversation because the evidence is fragmentary. You can think of it like trying to reconstruct a conversation heard through a thick wall. You might catch a few tones, maybe a word, but the meaning stays out of reach. Still, even these faint traces are enough to keep scientists searching, revisiting old sites, collecting new samples, and refining techniques to coax information from rocks that have been squeezed, heated, and altered over billions of years. Some layers do yield microscopic remnants, tiny grains or chemical signals that hint at biological or environmental processes. These hints are often debated, reinterpreted, or revised, but each contributes a little more context to the broader mystery. As with so many questions about Earth's distant past, the search itself becomes part of the narrative. You can picture scientists walking carefully along exposed cliffs, brushing away debris to reveal another slice of ancient rock, hoping for a detail that changes everything, or at least nudges the story forward. It's a slow process, matching the slow rhythm of today's quiet discussion, and it reminds us how patient we must be when studying a planet that measures time in eons rather than years or decades. This opening exploration is only the beginning of the journey. There's much more to settle into about what the Earth might have been like during this silent stretch, and why the record feels so faint. But for now, let's ease gradually toward the deeper layers of the puzzle, letting the shapes of vanished worlds, missing clues, and shifting landscapes settle softly into place as we move ahead. The deeper we move into this investigation of vanished ages, the more the rocks begin behaving like reluctant storytellers. You would think layers that have been pressed together for hundreds of millions of years would be eager to share whatever they remember, but as scientists approach the period we're focusing on, the rocks grow noticeably quiet. Ordinarily, the Earth provides clues generously, almost as if the planet itself enjoys being studied. A layer of sandstone hints at old shorelines. A thin line of volcanic ash marks a sudden eruption. Fossils capture the shapes of creatures as vividly as if they were frozen moments waiting for someone to rediscover them. Yet within this particular span of prehistory, that dependable trail of information thins until it feels less like a transition and more like walking into a long hallway where the lights have been turned off one by one. It's an odd sensation, even for researchers who spend their careers navigating what is missing rather than what is present. Most of the time, gaps in the rock record are easy to understand. A river might have swept away sediments, or a region might have remained underwater for so long that nothing substantial accumulated. But the silence we're exploring isn't confined to one corner of the world. It shows up in places separated by oceans, continents, and vast stretches of time. You could travel from Australia to North America, from ancient cratons in Africa to mountain ranges in Europe, and still find the same bewildering absence. It's as if the Earth took a long pause in recording its own story, leaving only the faintest marks behind for us to puzzle over. Scientists often describe these gaps using terms that sound technical, but reflect surprisingly human challenges. They call them unconformities, surfaces where older layers are abruptly overlain by much younger ones. They know the missing interval existed, yet the evidence for it has been stripped away or never deposited in the first place. But this particular example stands out because the missing years aren't just a minor edit in the timeline. They stretch over spans long enough that entire ecosystems could have risen and fallen without leaving more than a trace or two behind, and when researchers try to reconstruct what happened, the silence in the rocks forces them to confront how easily entire chapters of deep history can slip out of reach. To picture what this silence looks like, imagine standing before a towering cliff of layered stone. Each band marks an ancient seabed, a desert, a swamp, or an environment that once existed. Some layers contain the shells of small marine creatures. Others hold impressions of ripples made by currents long gone. Above one layer you might find evidence that oxygen levels change dramatically, perhaps shifting the balance of life across the globe. But then, as your eyes travel upward, a sudden boundary appears. Below it are sediments from a familiar period. Above it are layers that belong to a much later age. Between them lies the missing time. Not literally a gap you can see, but a difference so stark that you can sense millions of years are unaccounted for. This kind of gap doesn't behave like a quiet interval where nothing much occurred. Instead, it resembles a chapter removed before the book reached the printer. Researchers expect to find transitions, gradual changes, or at least signs that old environments slowly gave way to new ones. Instead, they find abruptness, like a film whose middle reel has vanished, leaving two scenes stitched together despite clearly belonging to separate moments in the story. And because the Earth rarely produces such sharp boundaries without reason, the absence itself becomes a clue that something substantial affected the planet's surface during that time. Some scientists approach the problem by studying erosion. Perhaps during this mysterious interval, broad regions of land were exposed to intense weathering. Wind could have stripped away sediments. Rain might have dissolved layers. Rivers could have carved landscapes and carried sediments far from where they originally formed. Over millions of years, these processes can erase entire worlds one grain at a time. But the more researchers examine these surfaces, the more they notice that the degree of erosion doesn't match ordinary patterns. There are signs that the rocks were exposed for unusually long periods, in some cases so long that chemical reactions altered the minerals from the inside out. This level of alteration suggests conditions that were stable, yet strangely empty, as if the planet maintained a surface ready to preserve evidence, but the evidence either didn't form or was removed almost immediately. Another possible explanation involves sea level changes. If the oceans retreated worldwide, vast continental shelves could have been left exposed. These regions usually accumulate sediments that form rich fossil beds, but during a massive retreat, erosion would dominate instead of deposition. That would leave behind surfaces where life certainly existed, but the sands and muds that would have recorded it washed away before they had a chance to harden into rock. Yet even this idea raises more questions. Sea level changes are common throughout Earth's history, but they usually leave behind distinct markers such as shoreline deposits or chemical signatures in remaining sediments. In this interval, those markers appear inconsistently or not at all. The silence persists, even where rising and falling seas should have left at least a whisper of their movement. The most puzzling aspect is that when these missing layers end and the geological record becomes reliable again, life seems to have shifted. Fossils above the gap often show new characteristics, new patterns of organisation, and in some cases new forms entirely. It's not a dramatic shift like the kind seen after major extinctions. It's more subtle, like a gentle rearrangement. Yet without the layers that should document the transition, scientists struggle to determine whether this was a gradual process hidden by erosion or a sudden development triggered by something we can no longer identify. The silence leaves the timing uncertain and the sequence unclear. This leads some researchers to wonder whether the gap reflects a major environmental transformation. Perhaps global temperatures changed in ways that made fossil preservation unlikely. Extreme heat or cold could disrupt sediment formation, leaving few layers to record the presence of life. Chemical changes in the oceans might have dissolved shells or prevented minerals from forming properly. Even small shifts in chemistry can erase delicate structures before they fossilize. If these conditions persisted for long periods, the result would look very much like what we find today, a nearly blank stretch in the rock record that defies easy explanation. Despite the challenges, scientists continue to look for small clues hidden within the silence. Sometimes a thin streak of mineral deposits suggests that volcanic ash settled on an exposed surface before being washed away. In other cases, microfossils appear in unexpected places, hinting that life persisted even when larger organisms left no trace. Chemical analyses may show subtle shifts in isotopic ratios, implying changes in atmospheric or oceanic conditions. These details are often faint, the kind of evidence that requires extremely sensitive instruments to detect. But even the faintest signals help researchers narrow down what might have happened. Interestingly, regions that were once deep underwater often show fewer signs of this gap than regions that were higher and drier. This suggests that the missing record might be tied to environmental boundaries between land and sea. Areas near ancient coastlines appear particularly affected, supporting the idea that sea level fluctuations or climate-driven erosion have played a major role. But once again, the pattern is not consistent enough to provide certainty. Some coastal regions preserve more detail than expected, while some inland areas have missing layers that are hard to explain. The silence doesn't fall evenly. It behaves almost like a patchwork, with some sections preserved by chance and others wiped clean by forces we still cannot fully identify. And so, the mystery grows. Not because the rocks mislead us, but because they show just enough information to make it clear that something unusual happened. What that something was remains open to interpretation. Some researchers lean toward environmental causes, others consider biological explanations, wondering whether life at the time was dominated by organisms too soft or too fragile to fossilize reliably. There are also tectonic theories. Perhaps the continents themselves shifted in ways that rearrange habitats faster than fossils could accumulate. Continental uplift can raise entire regions, exposing them to erosion and creating unconformities across great distances. If this happened repeatedly or slowly enough, it could create a long, drawn-out interval where sediments never had time to settle. Yet even tectonics cannot fully explain the global scope of the silence. Movements that large tend to leave scars in the form of mountain ranges or widespread igneous activity. Some signs do exist, but not in amounts that match the magnitude of the missing record. It's more like a long period where the Earth simply failed to record its own experiences even though life and geography were certainly active. This leads to one more possibility scientists consider, though cautiously. The gap might result not from a single cause, but from a combination of several. Perhaps sea levels fluctuated while continents moved. Maybe erosion was intense in some regions, and chemical conditions prevented fossilization in others. Microbial life might have dominated, leaving minimal physical evidence. When multiple processes act together, their combined effects can produce outcomes far more dramatic than any one cause alone. And over millions of years, even subtle influences can reshape the entire geological record. What makes this all so fascinating is how differently we must think when dealing with deep time. In everyday life, a missing detail can be corrected quickly. But when exploring billions of years, a missing detail might represent entire landscapes, climates, or ecosystems that vanished before leaving more than a whisper behind. The rocks can only tell us what survived long enough to be recorded. Anything fragile, unstable, or unlucky may have slipped out of the narrative entirely. The silence reminds us that Earth's story is incomplete, not because the planet is deliberately hiding information, but because preservation depends on countless circumstances aligning in just the right way. If we could stand on the surface of the Earth during that missing interval, the world would not have appeared blank or silent. Wind would still have moved across plains and coastlines. Waves would have broken on shores. Microbes would have grown in shallow pools. Early organisms might have floated through ancient seas. The sun would have risen and set each day, though the sky and atmosphere may have looked different depending on chemical conditions at the time. Everything would have been active, dynamic, and alive in its own way. The blankness exists only in our record, not in the reality of the past. Recognizing that distinction brings a kind of calm perspective. Not everything that matters leaves traces, and not every moment survives long enough to be studied. That doesn't make the missing spans less important. If anything, it underscores how fragile evidence can be when measured against the vast scale of geological time. The silence becomes a reminder of how much lies beyond our ability to reconstruct, and how impressive it is that so much of Earth's history remains legible, despite all the forces working against preservation. Even within the scientific community, there is a growing appreciation for how much uncertainty surrounds these intervals. Instead of forcing the evidence to fit a single explanation, many researchers embrace the ambiguity, using it as motivation to refine techniques, search for new sites, and approach old problems from fresh angles. The missing record doesn't frustrate them as much as it inspires them to ask better questions. After all, science advances as much through curiosity as through discovery. The silence in the rocks becomes less of an obstacle and more of an invitation. It encourages us to imagine what the Earth experienced during that long stretch, not in a speculative or fantastical way, but in a grounded sense that recognizes the interplay between environment, biology, and geological processes. As we move further into this stretch of Earth's history, where the rocks begin to lose their confidence, it becomes useful to imagine what the world may have looked like before the record thinned so dramatically. Not in a way that leaps into fantasy, but through the careful lens of what we know about the periods before and after the missing interval. Those bookends, though separated by millions of years, give us a general sense of how life functioned during the earlier stages of evolution. By studying them closely, scientists attempt to infer what the world must have contained even when it left nothing behind to confirm it. The time before the disappearance in the geological record wasn't quiet or empty. Life existed, though much of it was microscopic and delicate. Microorganisms drifted through ancient oceans, coated rock surfaces, and formed layered microbial mats along coastlines and shallow seas. These life forms were simple by our modern standards, yet they shaped the environment profoundly. They altered the chemistry of oceans, influenced the composition of the atmosphere, and played a role in the slow rise of oxygen levels that later supported more complex organisms. Even though these creatures rarely fossilized, their influence can be seen indirectly in chemical signatures that mark the presence of biological processes. These earlier worlds also experienced significant environmental changes. Temperatures fluctuated, sometimes dramatically. Ice advanced and retreated in cycles that remain partly understood. Volcanic activity may have been frequent, filling the air and water with nutrients as well as hazards. Through it all, life persisted, adapting to pressures that would be considered extreme by many modern standards. It was a world defined not by stability, but by an ongoing negotiation between organisms and the environments they inhabited. That negotiation shaped the conditions that later forms of life would inherit. Because of these interactions, scientists expect that the interval right before the missing record should show signs of steady diversification. Microbial communities typically respond to environmental changes with noticeable shifts. Some groups flourish, while others decline. Chemical markers in sediments usually document these transitions clearly enough for researchers to detect broad patterns. But as the timeline approaches the gap, those patterns begin to blur. Layers that once recorded changes in oxygen levels or carbon cycling become more ambiguous. Sediments lose the fine distinctions that indicate shifting habitats. At first glance, the world before the gap appears to fade gradually, as if the systems that produced distinct geological signatures were losing contrast before the record vanished entirely. This doesn't necessarily mean life was struggling. It could mean that the conditions required for detailed preservation were beginning to weaken. For example, if sediments were forming more slowly or inconsistently, the environmental signals imprinted within them would become diluted. Alternatively, if erosion intensified before the gap fully formed, earlier signs of life and climate could have been partially erased even before the main interval was removed. The transition from a world that leaves clues to a world that slips silently into the past might not have been abrupt at all. It may have been a gradual decline in visibility rather than a collapse in activity. To understand this better, researchers examine places where earlier rocks do remain relatively intact. In some regions, the layers immediately below the gap show structures left behind by microbial communities. These structures, though small, indicate thriving ecosystems. Microbes can create domes or ridges in sediments that harden into stone over time. They can concentrate minerals into patterns that reflect their growth. Even if the organisms themselves rarely fossilize, their handiwork can survive. And in places where these features appear close to the missing interval, they show that life wasn't retreating. It was active, restructuring its surroundings day by day, leaving marks that would eventually be swept away along with everything else. Other clues come from the minerals themselves. Certain species of microorganisms influence which minerals precipitate out of seawater. By analysing the composition of ancient sediments, scientists can determine whether biological processes were actively shaping the environment. In some samples from just before the missing interval, these mineral signatures are strong. That means the oceans were chemically dynamic and probably hosted large microbial populations. Yet even these active systems left little behind once the gap began. It's as though the conditions that once allowed their influence to be preserved were suddenly altered, leaving only a faint memory of their existence. Another consideration is the geography of the continents at the time. Land masses were arranged differently than today, forming configurations that influenced climate, currents, and habitats. Some areas were shallow marine environments, ideal for preserving fossils and chemical records. Others were deep basins where sediments accumulated steadily. When researchers reconstruct these ancient landscapes, they sometimes find that regions rich in pre-gap sediments were becoming less stable as the missing interval approached. Tectonic forces could have begun lifting some regions or tilting others. If a shallow sea slowly drained or retreated, the once protected environment would have become exposed to erosion. That exposure could have lasted for millions of years, enough time to remove any trace of what once thrived there. Climate shifts may have compounded these changes. Even small variations in global temperature can affect weathering rates, ocean circulation, and nutrient delivery. The balance between erosion and deposition might have been altered subtly at first, then dramatically as conditions continued to change. When environmental systems approach tipping points, they can shift behaviours quickly. The world before the gap could have been edging toward instability, not in a catastrophic sense, but in a way that made preservation increasingly unlikely. The more unstable the environment became, the harder it would have been for sediments to settle gently enough to capture details of life. Despite these difficulties, the world before the gap wasn't shapeless. We know enough from earlier periods to describe certain broad characteristics. The oceans were likely home to numerous microbial species adapting to chemical gradients and nutrient availability. Some may have been capable of forming colonies large enough to influence the appearance of coastal regions. Others may have lived free floating in the water column, affecting oxygen production and carbon cycling. On land, if any emerged regions existed, microorganisms might have formed crusts on soil or rock surfaces, altering erosion patterns and contributing to the development of early terrestrial ecosystems. Even though these communities were simple, their collective effects were substantial. Life at that time also interacted with geological processes in ways we still observe today. Microbes can accelerate the weathering of rocks by producing acids or altering the chemistry of surrounding water. They can trap sediments, forming the earliest hints of soil. They can create conditions that favour the formation of certain minerals, leaving subtle but measurable traces. When we see these signs in older layers, we can reasonably assume that similar activities occurred before the gap formed. The challenge is that the gap prevents us from seeing whether these interactions changed in response to new pressures. Without the record, it's difficult to tell whether life was on the cusp of a major shift when the silence descended. Even so, a few narrow windows into the past remain. In certain isolated pockets, small fragments of rock lying just below the gap have escaped significant alteration. These rocks sometimes preserve tiny pieces of organic matter, carbon-based remnants that hint at living organisms. When researchers extract these remnants and analyse them, they find signatures that indicate biological activity was robust. The structures may not be distinct enough to identify specific species, but they show that ecosystems existed, even if the details are lost. It's a reminder that the world didn't lose its complexity. We simply lost the layers that would have allowed us to see it clearly. Some researchers approach the problem from another angle entirely. Instead of focusing on what the rocks fail to show, they focus on what they still contain. For example, certain isotopes can reveal whether photosynthesis was changing during that time. If oxygen production fluctuated, the isotopic record should reflect that. In some pre-gap layers, there are hints of variability that could suggest environmental stress or adaptation. These hints don't provide a complete picture, but they suggest that the period leading into the gap was one of transition. Not necessarily upheaval, but change significant enough to leave a faint imprint even before the main record disappeared. Researchers also examine how global patterns may have shifted before the gap. If ocean circulation changed, sedimentation patterns would change with it. Nutrient delivery might have varied, affecting which microbial species dominated. Weathering rates on land could have influenced the chemistry of rivers feeding into the ocean. All of these interconnected processes shape the geological record. If one or more change direction, the world before the gap may have entered a phase where the usual processes of preservation no longer applied. That wouldn't erase life itself, but it would erase its traces, which is what we see today. When we think about these vanished worlds, it's easy to forget that life at the time wasn't limited to isolated pockets. Microorganisms tend to spread widely, colonizing environments wherever conditions allow. Entire coastlines may have been lined with microbial mats, shifting in shape and density as tides and currents changed. Shallow seas may have contained populations large enough to alter global chemistry. The world was alive, but in a manner that didn't favour durable fossilization. The absence of evidence isn't an absence of life, it's simply a reminder that life's earliest forms were too fragile to endure the forces that later erased the record. This fragility raises another question. Could these early communities have experienced pressures that prepared them for the evolutionary changes seen after the gap? Possibly. Environmental stress can drive adaptation. If the world before the gap was undergoing shifts in temperature, chemistry, or nutrient distribution, microbial populations might have diversified or reorganized in ways that set the stage for later developments. The gap prevents us from observing these transitions directly, but circumstantial signs suggest that life was responding to pressures we can no longer trace precisely. Even the landscapes themselves may have played a role. If continents were slowly drifting into new positions, they could have altered global currents or changed climate zones. These shifts can influence everything from coastal erosion to the distribution of sunlight across the planet. The world before the gap might have been in motion, not in a dramatic sense, but in a slow, persistent drift that gradually transformed its character. These transformations leave marks in the rock record, unless the record vanishes, which is exactly what complicates our understanding of this period. Yet, despite all these uncertainties, there is comfort in knowing that the world before the gap wasn't defined by emptiness. It was full of interactions, both biological and geological. Its seas supported thriving microbial ecosystems. Its coastlines were dynamic, shaped by tides and currents. Its atmosphere was changing in ways that would eventually enable new forms of life to emerge. Even though the details of this world are mostly gone, the broader outline remains visible enough to show that life had already become a force capable of influencing its surroundings. In moving further through this inquiry, we're reminded that the disappearance of evidence doesn't diminish the importance of what took place. The vanished worlds before memory began may be hard to reconstruct, but they laid the groundwork for everything that followed. As the missing stretch of Earth's history comes into clearer focus, even if only through its absence, one question emerges naturally. If entire worlds vanished from the rock record, what happened to the life that lived within them? The periods before and after show signs of biological activity, and the chemical clues that do exist suggest that organisms were present throughout. Yet when researchers search for fossils or even faint outlines of ancient life forms, from within the gap itself the rocks respond with a steady silence. Not a refusal exactly, but an inability. Whatever lived during this span seems to have moved through the world without leaving the durable traces we associate with the past. Understanding why requires stepping into the realm of creatures whose existence was real and active, yet so delicate that time erased them completely. When most people think of prehistoric life, they imagine bones or shells, or at least something large enough to be seen without special equipment. But for most of Earth's early history, organismal life was not built to endure the geological pressures that create the fossils we rely on today. Before animals developed skeletons or tough exteriors, life was primarily soft-bodied, microscopic, or built from materials easily broken down by environmental processes. Even organisms abundant enough to influence global systems were often so fragile that their remains dissolved long before fossils could form. Entire lineages may have lived and disappeared without leaving more than a faint chemical trace, if even that. These early organisms did not move through their environments in ways that produced obvious marks. They did not leave footprints in the sense familiar to us. They had no bones that could fall into sediments, no shells that could calcify into durable structures, no rigid parts that resisted decay. Their bodies broke down quickly, whether in the water column, on the sea floor, or along the margins of microbial mats. If they died in regions where sediments formed slowly or inconsistently, decomposition outpaced burial, leaving nothing behind. Even in cases where burial did occur, the conditions needed to mineralize soft tissues were rare and unpredictable. This lack of preservation does not imply that life was scarce. In all likelihood, life was widespread, particularly in the oceans. Early ecosystems were dominated by microorganisms that thrived in environments shaped by nutrient availability, sunlight, and chemical gradients. These organisms interacted constantly with their surroundings, cycling nutrients and altering water chemistry. Their influence remains detectable in isotopic patterns observed in some older rocks, but these signatures tell us only that life was present and active. They offer little insight into what specific organisms existed or how they interacted with one another. Even beyond microbes, there may have been early multicellular organisms with bodies so soft and transient that they vanished without a trace. Evidence from periods well before and well after the gap shows that such creatures did evolve at various points in Earth's history. Some resembled simple sheets or filaments, others may have floated through shallow seas. Their shapes and behaviours remain largely speculative, because these organisms only fossilize under exceptionally rare conditions that the missing interval seems not to have provided. In the absence of direct evidence, scientists study the surrounding context to understand the kinds of organisms that might have existed. They examine the chemical composition of surrounding layers, which sometimes indicates shifts in oxygen levels or carbon cycling patterns. When these shifts occur abruptly across the boundaries of the missing interval, it suggests that biological processes were changing. These changes could reflect the emergence or disappearance of entire groups of organisms too fragile to be preserved. One possibility is that new life forms evolved during this time, but lacked the structural features necessary for long-term preservation. Evolution does not proceed with equal speed across all traits. Organisms may have undergone important genetic or metabolic innovations that did not immediately translate into fossilizable structures. The world might have been full of creatures experimenting with new ways of existing, none of which left behind the durable remains needed for scientists to identify them today. Another possibility is that existing organisms diversified or adapted to new ecological pressures. Environmental changes often drive shifts in community structure, even among microscopic species. If nutrients became more scarce in some regions, certain organisms might have developed ways to store energy more efficiently. If chemical gradients shifted in the oceans, new metabolic pathways could have emerged. These innovations would affect the entire ecosystem, even if the organisms involved remained too fragile to fossilize. Over time, these subtle transitions could have set the stage for more easily preserved life forms that appear after the gap ends. Researchers also consider the environments these organisms would have inhabited. If the missing interval experienced fluctuations in water depth or sedimentation rates, entire habitats could have been unstable. Shallow seas may have expanded and contracted. Coastal regions might have faced exposure in some periods and inundation in others. These unstable conditions challenge the formation of continuous sedimentary layers, making fossilization nearly impossible. Even organisms that lived in large numbers would not have left clear records if they inhabited regions prone to erosion or chemical dissolution. What makes this particularly challenging is that the environments best suited for preserving soft-bodied organisms, such as low-oxygen basins with consistent sedimentation, appear not to have been widespread during the gap. Instead, the geological evidence points toward environments where decomposition rapidly outpaced burial. Even if countless organisms inhabited these areas, their remains would have broken down before sediments could bury them deeply enough to escape physical or chemical destruction. Some researchers turn to microfossil studies to find any survivors of this vanishing world. Microfossils, often made of durable materials like silica, can preserve the shapes of tiny organisms, but even they are scarce in this interval. In a few rare cases, microscopic structures do appear, but they are often so fragmented or altered that their biological origins remain uncertain. These occasional fragments are like the last faint echo of a conversation whose participants stepped away long ago. They hint at complexity but stop short of revealing clear identities. Chemical fingerprints provide another avenue of investigation. Certain organic molecules survive longer than physical structures and can indicate the presence of specific groups of organisms. But molecules can migrate through rocks or degrade over time, making interpretation difficult. Even when chemical signatures suggest biological activity, they rarely convey the diversity or characteristics of the organisms themselves. They merely confirm that life continued during a time when the planet chose not to record it clearly. This difficulty makes the silence of the gap more striking. Life almost certainly filled the oceans and perhaps small pockets of land, but it passed through the world like mist, leaving no sturdy memory of its presence. The creatures without footprints did not vanish because they were rare or unimportant. They vanished because their nature and their environments did not favour preservation. Their absence in the rock record is not an indication of their insignificance. It is an artifact of time, chance, and the fragile materials from which early life was made. Some scientists propose that these organisms may have been experimenting with structural innovations that eventually made fossilization more likely. The development of rigid cell walls, protective coatings, or early mineralized structures could have begun during the gap. These features, once established, would appear in the fossil record as soon as they became common enough to leave remains in sediments. The organisms living during the gap may represent transitional forms whose features were too early in their development to fossilize consistently. If so, they were the quiet precursors to the more recognizable forms that appear after the missing interval ends. Understanding these vanished life forms requires a shift in mindset. When we imagine the past, we often think in terms of the tangible, bones, shells, hardened impressions. But the majority of life in Earth's history has not been built to leave such legacies. The creatures living before and during the gap were part of continuous processes that shape the planet, even if they did not preserve themselves within it. Their contributions influenced atmospheric chemistry, nutrient cycles, and the stability of early ecosystems. They participated in networks of interaction, even though they left nothing behind for us to observe directly. Even in their disappearance, however, these organisms reveal something important. Their lack of traces shows that preservation is not a passive process but a rare convergence of conditions. For a fossil to form, an organism must be buried quickly enough to avoid decomposition, protected from erosion, and ultimately subjected to geological processes that transform sediments into rock without destroying what lies within. Any disruption to this sequence can erase an organism's entire existence. During the missing interval, disruptions appear to have been common, whether from climate shifts, erosion, chemical instability, or simply the fragile nature of the organisms themselves. Despite this, scientists remain optimistic about uncovering new hints. Advances in imaging and molecular analysis continue to reveal previously undetectable evidence in older rocks. Techniques that examine the structure of minerals at microscopic scales can sometimes identify patterns created by biological activity. Experiments simulating early environments help researchers understand how certain types of organisms might degrade or preserve under different conditions. Each method brings a clearer sense of what might have lived during the gap, even if the creatures themselves remain invisible. There is also the possibility that exceptional sites exist somewhere waiting to be found. In other periods of Earth's history, rare deposits have preserved soft-bodied organisms in remarkable detail. These sites often occur in places where unusual conditions halted decomposition. If a similar site exists for the missing interval, perhaps in a region not yet surveyed or beneath layers of rock not yet examined, it could shed unprecedented light on the creatures that once lived without leaving footprints. The absence of evidence today does not preclude the possibility of future discovery. For now, the creatures that lived during this vanished period occupy a kind of conceptual space. They are inferred from the patterns they influenced and the transitions that followed, but their specific forms remain unknown. Their invisibility emphasizes the delicate balance between life and the record it leaves behind. Most organisms, even today, will never fossilize. They contribute to the world in ways that cannot be preserved in stone. The creatures without footprints belong to that vast unseen majority, active participants in Earth's evolving systems, but silent in the timeline we use to study them. Even without physical remains, these organisms matter because they shaped conditions for the life that followed. They helped build the chemical foundations of the oceans. They influenced atmospheric changes that later supported more complex evolution. They interacted with the environment in ways that created new possibilities. Their invisibility doesn't diminish their role. Instead, it highlights how much of life's story occurs outside the narrow lens of fossilization. As the record gradually reappears after the gap, the organisms that emerge seem different enough to suggest that something meaningful happened during the interval. Whether this reflects evolution, extinction, or simply the difference between preserved and unpreserved forms remains uncertain. But it's clear that the gap marks more than a missing layer of rock. It marks a missing chapter of biological innovation. As we follow the fading trail of evidence into the heart of the missing interval, the mystery widens from the silence of individual organisms into something far larger. It becomes clear that the loss isn't limited to fossils or fragile life forms, but extends to the very rocks that should have carried their stories. The planet behaved differently during this span, not simply failing to preserve details, but failing to record them at all. It's as if the Earth moved through a long stretch of time without keeping track of its own experiences, leaving a blank instead of a layered, continuous account. The gaps don't appear randomly. They show up in places where steady sedimentation ought to have occurred. They interrupt sequences that seem otherwise reliable. They behave as though the world paused in its usual habit of writing history into stone. For scientists accustomed to reading rock layers like a book, this presents a fundamental challenge. Normally the Earth offers at least some kind of record even when the details are faint. But during this particular interval, the lines become nearly impossible to follow. In some regions, entire millions of years are missing between adjacent layers. In others, deposits thin until they resemble a brief pause instead of a long expanse of time. These inconsistencies make it difficult to reconstruct even basic environmental conditions. Instead of patterns that connect smoothly from earlier to later periods, there is a break where the usual geological storytelling simply stops. This break forces researchers to ask why the Earth stopped recording. Not whether life existed, but why the physical processes that capture life's traces cease to function in the way they usually do. Sediments accumulate when water, wind, or gravity deposit material faster than it erodes. Fossils form when organisms are buried quickly enough for decay to be slowed. Geological layers build up steadily when environmental forces are balanced. But during this missing span, these balances appear to have shifted. In some cases, erosion seems to have dominated completely. In others, deposition slowed to a crawl. In still others, layers may have formed only to be removed soon after, leaving nothing to mark their brief presence. To understand this better, researchers analyse how different regions of the world behaved during periods before and after the missing interval. Before the gap, many continental shelves show evidence of continuous sedimentation. Shallow seas covered large areas, and these environments typically produce thick layers of rock rich in chemical and biological clues. After the gap, sedimentation resumes in new patterns, reflecting changes in sea level, tectonic activity, and climate. But within the gap itself, something interrupted this natural progression. The Earth did not uplift suddenly across all regions. Sea levels did not fall uniformly. Climate did not reach such extremes that deposition became impossible everywhere, and yet the record fails consistently enough that it cannot be dismissed as coincidence. This raises the possibility that multiple small shifts acted together. Perhaps certain areas experienced increased erosion from climate variability. Perhaps rising or sinking crust altered where sediments accumulated. Maybe biological activity changed the chemistry of the oceans in ways that influence sediment formation. When these kinds of processes overlap, they can produce a global pattern without requiring a single dramatic event. The planet might not have experienced catastrophe at all. It may have simply slipped into a combination of conditions that made record-keeping ineffective for a time. One piece of this puzzle comes from studying surfaces that lie directly beneath younger layers. These surfaces often show signs of exposure. They may contain features created by weathering rather than deposition. Some show chemical alterations suggesting they were open to air or shallow water for long periods. Others show small-scale structures that form only when sediments are repeatedly disturbed. These signs indicate that, instead of accumulating new layers, the Earth's surface in these regions was subjected to prolonged erosion or inactivity. It's as though the planet was unable to settle long enough to write anything down. Such surfaces are found across multiple continents. While they vary in detail, they share a common character. They represent a missing span of time rather than a single event. Their formation would have required stability on the surface, but not the kind that encourages preservation. Stability in this context means that the surface remained exposed rather than buried. Exposure for millions of years would allow rain, wind, and chemical reactions to remove traces of earlier layers and prevent new ones from forming. This ongoing exposure could explain why so little remains from the interval. However, exposure alone does not explain everything. For these relationships to hold across different continents, global processes must have influenced local environments. Climate shifts are one candidate. Even moderate changes in precipitation, temperature, or wind patterns can affect how sediments accumulate. If these conditions persisted long enough, they could reshape landscapes around the world. But climate alone rarely produces global erosion, without leaving other distinct markers. Researchers continue to search for consistent chemical signatures that would confirm a widespread climatic influence. So far, the evidence remains suggestive rather than definitive. Another factor might be the movement of tectonic plates. Continents drift slowly but steadily, and their movement changes patterns of uplift and subsidence. If certain regions were rising slightly during this interval, they would experience increased erosion. If they were sinking only weakly, deposition might have been too slow to preserve much. Yet again, the difficulty is that tectonic shifts tend to leave clear structural evidence, and while some features correspond to the missing interval, they do not fully account for its scope or consistency. Some researchers look instead to biological influences. Microbial life can play a surprisingly significant role in the formation and destruction of sediments. Microbes contribute to the precipitation of minerals, the stabilization of sediment surfaces, and the cycling of nutrients. If microbial communities shifted in composition or abundance during the gap, these changes might have altered how sediments formed. Certain groups of microorganisms can dissolve minerals rather than precipitate them. If such groups became prevalent, they might have prevented sediments from hardening into rock. This idea aligns with evidence that biological processes were active during the missing interval, even if they did not leave direct fossil traces. The difficulty with this explanation is that microbial influence alone cannot erase large amounts of sediment. It can disrupt preservation, but it cannot remove layers that already exist. For that, physical erosion or geological movement is required. Still, microbial shifts may have been part of a broader pattern, influencing what could be preserved even as other forces shape the surface. Another aspect worth considering is sea level fluctuation. If global sea levels rose and fell repeatedly during the missing interval, coastal environments would have been unstable. Frequent flooding and exposure cycles can prevent long-term sediment accumulation. Shallow seas can shift rapidly, redistributing sediments instead of burying them. While such fluctuations would not leave clean, uninterrupted layers, they also would not necessarily produce widespread erosion. The combination of unstable coastal regions and slow sedimentation elsewhere could contribute to the patchwork of missing layers observed today. Even deep ocean environments may have been affected. While deep-sea sediments often accumulate steadily, tectonic and chemical conditions can disrupt deposition or promote later erosion. Submarine landslides can remove sediments across large areas. Ocean chemistry shifts can alter mineral formation and dissolution. These factors complicate the narrative further, suggesting that the Earth may have been going through a phase when familiar processes were behaving differently, but not in a catastrophic sense. Rather, they operated in ways that reduced the likelihood of forming durable records. When researchers attempt to reconstruct this interval, they encounter a problem similar to rebuilding a story from a few scattered notes. They look for clues at the edges of the missing interval, comparing what came before with what came after. In many cases, there are indications that environmental conditions changed. These changes might include shifts in oxygen levels, differences in carbon isotopes, or new mineral phases that suggest altered chemistry. But without the layers from the interval itself, the transitions remain unclear. The planet seems to have moved from one set of conditions to another without documenting the path it took. This unexplained transition is one of the reasons the missing interval is so intriguing. Before the gap, the world exhibits certain characteristics. After the gap, new patterns emerge. The lack of continuity prevents scientists from tracing cause and effect across the boundary. Instead, they are left with two stable periods separated by an absence. That absence may represent change, stability, or something in between. Without the record, every possibility remains open. Some researchers compare this phenomenon to a system resetting itself, not in a dramatic or sudden way, but through a combination of small adjustments that accumulate over time. If enough environmental factors change gradually, the entire system can shift to a new state. The missing record may hide these adjustments, making it difficult to see how different influences converged. The Earth may not have forgotten to write its own story. It may have written it in a way that left no durable mark. In a broader sense, this missing record highlights how much of Earth's history is shaped by chance. The preservation of geological layers depends on an intricate balance of physical, chemical, and biological processes. If any of these processes shift even slightly, the likelihood of long-term preservation can change dramatically. The period we are examining appears to have occurred during a time when that balance favoured erasure over recording. The world continued to evolve, but the traces of that evolution were swept aside, altered, or never captured fully in the first place. When considering how many details can be lost so effortlessly, it becomes easier to appreciate the fragility of the geological record. Even though the Earth is vast and dynamic, the formation of lasting evidence requires remarkable precision. A sediment must accumulate quickly enough to bury remains. It must escape erosion long enough to transform into rock. It must survive tectonic forces, chemical alteration, and pressure for millions of years. Most organisms and environments fail at one of these steps. The missing interval reflects a time when nearly everything failed, not because life declined, but because conditions were poorly suited for preservation. Yet the Earth didn't stop evolving during this time. Its landscapes changed, its oceans shifted, its atmosphere likely experienced gradual modifications. Life adapted, interacted, and shaped its surroundings. The absence of preserved layers doesn't indicate inactivity. It indicates that the processes necessary to preserve those activities were not present. The planet was not silent. It was simply writing in a medium too fragile to survive. Even so, the missing record poses questions that extend beyond geology. It challenges the assumption that the past can always be reconstructed, given enough effort. It reminds us that Earth's history is incomplete, not because we lack skill or technology, but because the planet itself decides what remains. Understanding the missing interval requires accepting that some stories existed, even if the pages that contain them no longer do. What stands out most when researchers examine the periods surrounding the missing interval is not the presence of clues, but the strange pattern of where those clues suddenly stop. In many places, the layers leading up to the gap look normal, filled with the usual signs of shifting environments. They show changes in grain size, chemical composition, and the kinds of sediments that settled. Some hold faint biological traces or structures shaped by water movement, but after following these details upward through the rock, the signs begin thinning. They don't disappear all at once. Instead, they taper gradually, becoming less distinct, until the layers reach a surface that feels stripped clean. Above that surface, younger rock resumes as if nothing unusual occurred. This contrast makes the interval look like a chapter that was once present, and then erased carefully enough to remove most of its contents. Because the disappearance is so consistent across distant regions, scientists began comparing these boundary surfaces more closely. These surfaces are often smooth or gently uneven, signs that they were exposed for a long time before being buried again. On some, tiny fractures appear where water slowly seeped in, expanded minerals and altered their texture. On others, thin crusts formed when chemical reactions occurred between the rock and the atmosphere. All of these features imply that these surfaces sat at the top of the landscape for far longer than typical sedimentary layers do. Instead of being covered quickly, they remained open to the elements. That exposure contributes heavily to the loss of information. Anything deposited briefly on top of such a surface would have been washed away before it could accumulate reliably. One of the ways scientists try to understand these surfaces is by mapping how they vary from place to place. In areas where the gap is especially large, the boundary may appear more deeply weathered. In places where the gap is shorter, the surface may show fewer signs of prolonged exposure. This variation provides clues about how different regions behaved. For example, continents that sat closer to the equator during the gap may have experienced stronger rainfall or warmer conditions, accelerating erosion. Regions nearer ancient polar areas may have had less intense weathering, but still lack the steady deposition needed to build layers. These differences help scientists piece together how environmental forces shape the missing pages in Earth's geological book. A recurring question that emerges from these observations is why the planet did not simply continue depositing sediments during the interval. After all, even in dynamic environments, some areas usually record at least partial histories. Yet during this gap, those opportunities seem unusually rare. One explanation is that many regions were transitioning between different kinds of environments. For example, an area that started as shallow sea might have gradually risen until it became a coastal plain. During such transitions, sedimentation patterns can become erratic. Some years might bring deposition, while others bring erosion. Over millions of years, these alternations can cancel each other out, leaving little behind. Eventually, the land might have sunk again, allowing new sediments to cover the old surface, preserving only the eroded remnants of the earlier landscape. Another aspect worth considering is how sea level changes influence preservation. Sea levels rise and fall for many reasons: climate shifts, tectonic activity, and changes in the volume of ocean basins. During the missing interval, sea levels may have fluctuated in ways that repeatedly exposed and submerged coastal areas. These cycles disrupt sedimentation. When water rises, sediments may deposit quickly. When it falls, those same sediments may erode. If these cycles persisted over long spans of time, the result would be a surface that constantly reset itself. Such surfaces are notoriously poor at preserving fossils or consistent layers, which fits the pattern seen during the gap. Because erosion can remove enormous amounts of material without leaving much behind, the scope of the missing layers becomes easier to understand. Even a modest rate of erosion sustained over millions of years can strip away sedimentary packages thick enough to contain entire ecosystems. Once those layers are gone, later deposits cover the surface, sealing in the absence just as effectively as they would have sealed in a fossil bed. This creates the illusion that nothing happened during the interval, when in fact many things may have happened before being removed. The rocks directly above the gap add more context. In many places, these layers contain fragments of minerals that indicate new environmental conditions. Some show grains carried by rivers that did not exist before. Others show marine characteristics where land previously stood. These differences make it clear that environments shifted significantly across the boundary. The changes documented in post-gap layers reinforce the idea that the Earth was undergoing broader patterns of transition. These transitions, however subtle, could have played a major role in removing or preventing earlier sediments from forming. Part of the challenge in studying these missing pages is that the gaps affect multiple types of evidence simultaneously. Sedimentary textures fade, chemical signatures become ambiguous, fossil traces vanish almost entirely. Each line of evidence, if missing alone, might be explained easily. But when all disappear together, the mystery becomes more complicated. It suggests that the Earth's systems were operating outside the conditions that typically allow us to reconstruct ancient environments. Something about this interval disrupted every pathway through which information normally survives. This disruption may relate to changes in ocean chemistry. If seawater composition shifted during the gap, certain minerals would form differently. Some minerals help stabilize sediments, making them more resistant to erosion. Others contribute to cementation, the process by which sediments turn into rock. When those minerals become scarce, sediments remain vulnerable to later disturbance. Even slight chemical imbalances can prevent sediment from solidifying properly. If this occurred widely enough, many regions might have accumulated sediments that never hardened, making them easy targets for removal long after their deposition. At the same time, biological activity in the oceans could have influenced how sediments formed. Microbial communities can bind particles together, stabilizing surfaces. They can also break down organic matter, releasing chemicals that alter sediment composition. If microbial behavior changed during the missing interval, the kinds of sediments produced might have shifted as well. These interactions make it difficult to evaluate the absence of fossils because the conditions that normally favour fossilization may not have been present. Some researchers also look at global tectonic patterns during the gap. The movement of continents can tilt landscapes subtly. Even small amounts of uplift can expose large regions to erosion. Conversely, gentle subsidence may allow sediments to accumulate, but only if the rate of subsidence matches the rate of deposition. If tectonic movement was inconsistent, lifting some areas while lowering others, the resulting surfaces would reflect these competing forces. The variability in the thickness of missing layers across different regions supports the idea that tectonic processes played a role, even if they were not the sole cause. What complicates matters further is that the missing interval appears not as a single event, but as a widespread phenomenon that unfolded differently depending on location. In some places, the gap spans tens of millions of years. In others, it is shorter, but still significant. This variation suggests that the planet did not undergo one uniform shift, but rather a set of overlapping changes. The result was a global mosaic of environments that shared one common trait. They were poor at preserving geological history. Yet despite all these erasures, hints still surface at the boundaries. Pebbles of older rock sometimes appear within younger layers, evidence that erosion carried fragments into new settings. These reworked materials provide indirect clues about what once existed. They may contain chemical signals or altered minerals that preserve faint traces of environmental conditions. Although they cannot reconstruct the full picture, they offer reassurance that the Earth did contain more information before it was removed. Another way scientists approach the mystery is by studying locations where the gap is unusually small. These rare pockets act as windows into the missing interval. Though incomplete, they contain a few layers that escape destruction, long enough to leave behind thin records. These layers often show transitional features, sediments that reflect environments shifting gradually rather than abruptly. In some cases, these records include hints of biological activity, though rarely in recognizable fossil form. Instead, chemical gradients or mineral textures imply that life continued to interact with the environment. These isolated remnants strengthen the idea that the gap represents not a lifeless period, but a period in which preservation failed on a broad scale. As researchers compare these scattered remnants, certain patterns emerge. They suggest that the interval may have included multiple phases. Some regions indicate prolonged exposure. Others show brief episodes of deposition that were later erased. Some suggest calm environments where nothing accumulated. Others show signs of energetic conditions that moved large amounts of sediment. The result is a patchy record that varies dramatically from place to place, yet remains unified by its overall lack of durability. Because geological processes operate over immense timescales, even subtle changes can have enormous effects. A small shift in rainfall patterns could alter erosion rates enough to remove an entire sequence of layers. A slight variation in ocean circulation might prevent sediments from settling consistently. These small shifts, sustained across millions of years, can produce the kind of missing record seen during the gap. The Earth did not need dramatic disasters to erase its own story. It needed only a combination of normal processes occurring in unusual alignment. For many scientists, the appeal of this mystery lies not in its difficulty, but in what it reveals about the planet's sensitivity. The missing interval shows that Earth systems can change in ways that disrupt the usual methods we rely on to understand the past. It reminds us that the geological record is not a perfect archive but a selective one, shaped by the interplay of countless forces. What survives depends on the luck of preservation as much as on the events themselves. This understanding encourages researchers to refine their methods. They search for subtle signatures that might endure even when layers do not. They examine the structure of minerals at microscopic scales, looking for patterns created by environmental conditions. They use geochemical tools capable of detecting faint isotopic variations. Each new technique expands the possibility of uncovering fragments of the missing story, even if the full narrative remains out of reach. While the blank pages of this interval may never be filled entirely, they continue to influence how scientists interpret the periods before and after it. The absence forces a more cautious approach to reconstruction. It encourages humility about what can be known, and creativity in how to explore what cannot. The missing record becomes part of the story rather than a failure in the evidence. It shows how a planet can move through a long stretch of time without leaving behind the layers that usually guide us. Hints of dramatic events sometimes appear not in what the rocks show, but in what they fail to show. When researchers look closely at the periods before and after the missing interval, they occasionally notice signs that something disruptive may have unfolded during the gap, something significant enough to alter conditions without leaving the kind of physical evidence normally associated with major events. These signs don't point clearly to a single cause. Instead, they gather faintly, like a group of distant voices describing an incident none of them saw directly, but all felt indirectly. The rocks following the gap often contain traces of altered chemistry or reorganized ecosystems, yet the gap itself remains empty. If disturbances occurred during that time, they seem to have swept across the planet without preserving the usual signatures. This absence raises an intriguing possibility. Perhaps cataclysms did take place, but the circumstances prevented them from being written into stone. To understand why a cataclysm might leave no obvious geological record, it helps to consider how such events typically appear. Large-scale volcanism usually produces thick layers of ash or lava flows. Meteor impacts create craters, shocked minerals, or scattered debris. Sudden climate shifts can leave isotopic anomalies or mass extinction layers filled with fossils, but these markers depend on conditions that allow them to survive long-term. If those conditions did not exist, or if later processes removed them, the evidence could disappear just as completely as the fossils within the gap. A cataclysm might have occurred exactly where preservation was least effective, or it may have unfolded in ways that left no lasting trace even if its effects rippled across ecosystems. One category of possibility involves climatic instability. A shift long enough or severe enough could have altered sea levels, weather patterns, and sedimentation. For example, prolonged cooling might have caused glaciers to expand across high latitudes, grinding down surfaces that might otherwise have preserved sediments. Warming could have intensified storms, increasing erosion across entire regions. These effects would not necessarily leave clear indicators if subsequent erosion or deposition removed them. Instead of a clean boundary, they might create a long-term failure of preservation. A cooling event could also trap carbon in ways that disrupt the usual isotopic signals. If carbon cycling shifted dramatically, rocks after the gap might show different ratios of isotopes, while the gap itself holds no layers capable of recording the transition. Some studies have found small isotopic shifts before and after the missing period, suggesting the possibility of altered atmospheric or oceanic processes. These changes may hint at stresses affecting life, even though the rocks that should document the initial shift are gone. Another possibility is that rising oxygen levels during the early history of the planet reached a threshold that influenced biological and chemical systems. Oxygenation events are known to have occurred at several points in Earth's past, each reshaping ecosystems and influencing which groups of organisms dominated. If a similar event occurred during the missing interval, but was slow or uneven, it might not leave the distinct iron formations or chemical markers seen in earlier oxygenation events. Instead, it might leave only subtle changes detectable in younger rocks. Such a shift could have disrupted ecosystems, contributing to biological turnover without preserving the transition clearly. More abrupt disturbances are also considered. Some scientists wonder whether smaller meteor impacts could have occurred during the interval. While massive impacts tend to leave clear signatures, smaller ones might not. They could disrupt climates temporarily without leaving a crater large enough to persist. Over millions of years, craters erode, sediments shift, and any debris becomes incorporated into younger layers or washed away entirely. If multiple small impacts occurred within the gap, their cumulative effect could influence climates or ecosystems, but their individual signatures might never survive. Volcanic activity presents another pathway. Instead of large eruptions producing thick layers of ash, the missing interval may have seen prolonged but inconsistent volcanism. Low-intensity eruptions over long spans can release gases that alter atmospheric chemistry without leaving thick ash deposits. If such activity occurred during a time when sedimentation was erratic, the ash could have dispersed without accumulating, erasing both direct and indirect indicators. Volcanic gases can influence temperature, ocean acidity and nutrient cycles, affecting ecosystems in ways that would appear in later periods, but leave little in the interval itself. Even the possibility of tectonic reorganization plays into this theme. When continents shift, oceans open or close, and mountains rise or fall, the global environment changes. Such processes typically leave structural evidence, but the initial phases may not. A slow reorientation of ocean currents or the creation of new coastal regions can have far-reaching consequences for climate and sedimentation. If these changes began during the gap, they might have altered the planet's behaviour without leaving sharp geological boundaries. The later record reflects the results, but the early transitional stages remain hidden. It's also important to remember that cataclysms need not be explosive or sudden. Long-term environmental stress can reshape ecosystems gradually. For example, shifts in ocean circulation could have created regions with low oxygen or altered nutrient availability. These conditions can cause widespread biological change without direct geological markers. If the world experienced a prolonged phase of oceanic instability, ecosystems might have reorganized throughout the interval. Such reorganizations could appear as differences in the biological record before and after the gap, even though the transition is missing. This idea becomes more compelling when we examine how life behaves in times of gradual stress. Microbial communities respond sensitively to environmental pressures. If nutrient sources change or chemical gradients shift, community structures adjust. These adjustments may influence carbon cycling or mineral formation, producing signals that appear in younger rocks. Yet without fossils or preserved sediments from within the gap, it's impossible to determine exactly how these communities evolved. The biological turnover that appears after the gap could reflect either sudden change or long, steady adaptation. Without the intervening layers, the details remain hidden. While dramatic events are often considered, another important perspective is that the world may have experienced multiple moderate disturbances rather than one major one. A sequence of environmental fluctuations, none individually catastrophic, could add up to significant overall change. If erosion removed evidence of these fluctuations, their presence would still be implied by the altered conditions found in later layers. Many scientists favour this interpretation because it fits the scattered hints without requiring a single defining event. There is also speculation that early biological innovations might have influenced the planet in ways that mimic cataclysmic events. If certain microbial groups developed new metabolic pathways, they could have changed ocean chemistry significantly. These changes might modify sedimentation or alter mineral precipitation. For example, microbes involved in sulfur cycling can affect the formation of certain minerals that help preserve sediments. If those microbial groups expanded or collapsed during the gap, they might leave indirect effects in the rock record after the interval ends. Even though patterns in younger rocks suggest that something important occurred, the lack of preserved layers means researchers must use methods that detect influences rather than direct causes. Chemical gradients, mineral ratios, and isotopic shifts offer clues, but interpreting them requires caution. Similar patterns can result from different processes. Without the missing pages, the Earth's story during this period remains open to multiple explanations. To add to the challenge, later geological activity can distort or mask earlier signals. Rocks that formed immediately after the gap may have been buried deeply, heated, or chemically altered. These changes can blur details, making it harder to identify original conditions. When scientists examine these rocks today, they must determine which features are primary and which were added later. The possibility of altered evidence increases the uncertainty surrounding the nature of interruptions during the gap. Despite these complications, researchers continue investigating whether particular kinds of events might align with the patterns observed. For instance, some look for evidence of changes in volcanic gas output. Increases in carbon dioxide or sulfur dioxide can influence global temperature and ocean pH. These effects could disrupt ecosystems without producing thick volcanic deposits. While definitive proof is lacking, some chemical signatures in younger rocks are consistent with gradual atmospheric shifts. Others investigate whether tectonic movement may have altered ocean basins enough to disrupt global circulation. Ocean currents distribute heat, nutrients, and oxygen. If circulation patterns changed, marine environments could have been affected profoundly. These changes might not leave obvious geological markers if they occurred within regions where sedimentation was minimal. Researchers also explore whether biological innovations might have accelerated processes like weathering. Some microorganisms produce acids that break down rock. If these groups expanded during the gap, they could have increased erosion, contributing to the widespread loss of sedimentary layers. Even if the organisms themselves were not preserved, their influence might explain why geological pages from the interval are missing. Because the possibilities remain open, scientists often build models to test whether certain scenarios can produce the kinds of patterns observed. These models vary widely. Some simulate erosion rates under different climates. Others examine how ocean chemistry responds to gradual atmospheric change. Some focus on how microbial communities shift under variable conditions. By comparing model outputs to the limited evidence available, researchers aim to narrow the range of explanations. Every model has its limitations, of course. Without direct evidence, interpretations remain provisional. Yet the convergence of multiple lines of inquiry suggests that the missing interval was a time of significant transition, even if the nature of that transition is unclear. Whether through environmental instability, shifts in ocean circulation, biological innovation, or a combination of these, the planet appears to have moved into a new state during the gap. The younger rock layers reflect that new state, even though the path leading to it is largely invisible. One of the more intriguing aspects of this investigation is how it reshapes our understanding of Earth's resilience. The planet often absorbs disturbances without leaving explicit records. Ecosystems reorganize, climates adjust, oceans shift, mountains rise and erode. These changes can occur without producing the fossil-rich or sediment-packed layers we rely on for reconstruction. The missing interval provides a reminder that much of Earth's history may involve transitions too subtle, too dispersed, or too vulnerable to be preserved. This perspective also informs how scientists interpret other gaps. It becomes clear that the absence of evidence is not necessarily evidence of stasis or simplicity. Instead, it may reflect a dynamic world whose events outpaced or undermined the processes of preservation. The whispers of cataclysms, if they occurred, linger only in the altered states of what followed. Even though the missing interval conceals so much, the shift into the layers that follow brings new details into focus. They hint at reorganized environments, renewed sedimentation, and different biological patterns. These changes suggest the presence of forces that reshaped landscapes and ecosystems. Ideas about what might have existed during the missing stretch of prehistory often drift into territory that feels speculative, not because researchers want to imagine more than the evidence allows, but because the silence left behind creates space where many possibilities can fit. Some of those possibilities remain strictly within the boundaries of geology and early biology. Others stretch into broader interpretations, not in the sense of claiming advanced societies existed billions of years ago, but in exploring how early life might have organized itself in ways that blur the line between simple ecosystems and something more structured. Whenever people hear that a vast section of the rock record has vanished, it becomes natural to wonder whether the gap hides forms of life more complex than the typical microscopic organisms that dominate early Earth. While science has not found evidence for anything resembling advanced civilizations at that time, researchers do recognize that many evolutionary transitions could have occurred without leaving direct traces. These transitions might resemble early attempts at organized biological behavior, rudimentary, fragile, and entirely erased. Before moving deeper into these ideas, it's important to ground them in what scientists understand about evolution. Complex behavior does not require large bodies or durable structures. Microorganisms display cooperation, communication, and coordinated activity even today. They form layered communities that respond to environmental cues, share resources, and adjust behavior collectively. These interactions can create stable microenvironments that function almost like small societies. Yet because these systems consist primarily of soft, delicate organisms, they leave almost nothing behind in the geological record. If similar forms of early multicellular cooperation emerged during the missing interval, they could have altered ecosystems meaningfully without fossilizing. One line of thinking focuses on the possibility that early multicellularity might have begun experimenting with more integrated forms long before the fossil record shows clear evidence. In later periods, we see organisms developing structures that allow for division of labour, coordinated movement, and more complex metabolic strategies. These changes required earlier steps, many of which would not preserve well. The missing interval could have held experiments in biological organisation that set the groundwork for later innovations. Some of these experiments might have failed, leaving no descendants. Others could have survived but were too fragile or too rare to be captured in preserved sediments. The absence of fossils from the interval does not mean such developments did not occur. It simply means the conditions necessary to preserve them were not present. Researchers sometimes compare this period to other times in Earth's history when soft-bodied organisms dominated. Several well-known fossil beds capture such communities under exceptional conditions. These organisms were often numerous and diverse, yet nearly all other sites from the same periods remain empty. The lesson is that even when life is abundant, fossilization is incredibly selective. For the missing interval, the selectivity may have been even stronger. If conditions that favour soft tissue preservation were absent worldwide, entire evolutionary experiments could have unfolded unnoticed. These organisms might have formed colonies, networks, or mobility strategies that seem more advanced than earlier life, but lacked the structures needed to endure geological processes. Another idea sometimes discussed among scientists involves the possibility that early life forms may have achieved brief moments of complexity that did not last long enough to dominate ecosystems. Evolution does not always advance smoothly. It explores possibilities. Some branches flourish, others disappear quickly. During the missing interval, environmental pressures may have encouraged adaptations that pushed organisms toward more coordinated behaviour. If these adaptations offered short-term advantages but long-term vulnerabilities, they may have arisen and faded within the same span. Any such developments would be lost if erosion removed the sediments that captured their presence. While none of these possibilities resemble civilizations in the modern sense, they reflect the concept that life might have been experimenting with forms of organisation more advanced than simple microbial mats. Some researchers consider whether biological networks, structures formed by interconnected microorganisms, could have developed into more complex systems. These networks might have responded collectively to environmental changes, shared information chemically, or coordinated growth across large areas. Even today, microbial communities can communicate through chemical signalling, forming layers that behave cooperatively. If such behaviour expanded during the missing interval, it could have created ecosystems more structured than anything earlier. But without preservation, these brief steps toward complexity vanish from the record. Occasionally, discussions of the missing interval drift into imaginative territory among the public, where people wonder whether unknown ancient societies could have existed. Within scientific research, however, the focus stays grounded in the limits of biological possibility. Early Earth lacked the conditions for advanced civilizations as we understand them. The atmosphere, landscape, and ecosystems were not capable of supporting large organisms, let alone tools, structures, or technologies. What researchers do consider is whether complex behaviours, precursors to later evolutionary innovations, might have taken shape briefly. These would not involve intelligence recognisable to us, but they might involve collective growth patterns that hint at organisational experimentation. Another angle involves the potential for environments that encouraged rapid adaptation. When ecosystems face shifting conditions, changes in ocean chemistry, fluctuating temperatures, or unstable habitats, life often responds creatively. These responses can produce new traits or behaviours that spread quickly. But if the conditions shift again, these traits may disappear as rapidly as they arose. In a world where sediments are not being preserved, these bursts of innovation leave no record. The missing interval may contain numerous such bursts. Without layers to document them, all we see is the world before and the world after, each shaped by different conditions. Some scientists examine the geochemical hints that appear at the edges of the gap for signs of unusual biological activity. Certain isotopic anomalies could indicate shifts in how carbon was processed by living organisms. These shifts sometimes occur when new metabolic pathways evolve or when ecosystems reorganize. If a major biological transition occurred during the gap, it could have influenced global chemistry enough to be visible in later rocks. But since chemical signals can be altered, overprinted, or diluted, interpreting them requires caution. They offer hints rather than explanations. These hints inspire questions about how early life might have structured itself. For example, if larger colonies or early multicellular formations became common during the gap, they may have affected oxygen distribution within shallow seas. That in turn influences which groups of organisms thrive. A shift in dominant communities could cascade through ecosystems, producing the reorganized conditions seen after the gap. The lack of fossils means we cannot identify these organisms directly, but the changes they induced might survive as chemical or mineral evidence. A different set of ideas focuses on surface environments. If small patches of land existed during the missing interval, they might have supported early microbial soil crusts. These crusts can stabilize surfaces, influence erosion, and modify nutrient flow. If they expanded significantly, they might have shaped landscapes in ways that affected sedimentation. When such communities form today, they create distinctive patterns in soil chemistry. If similar patterns once existed during the gap, they would have been vulnerable to removal. Yet their influence on erosion could help explain why so much of the record from that interval disappeared. Discussions about what kinds of life existed during the gap also intersect with theories about early metabolic diversity. Life at that time may have been exploring different ways of harvesting energy. Some organisms might have used sunlight, others might have relied on chemical gradients. New metabolic strategies could have allowed certain groups to dominate temporarily. These strategies might have shaped ecosystems significantly, even though the organisms involved left no physical remains. If such strategies later disappeared, they would become another example of biological innovation erased by time. The most intriguing aspect of these ideas is how they highlight life's capacity for experimentation. Evolution is not confined to slow, gradual progression. It includes bursts of change, dead ends, and fleeting successes. During periods of environmental instability, evolutionary pathways may branch rapidly. Some branches survive, others vanish. The missing interval could have been filled with such branching. Without sedimentation to record these paths, we're left with only the outcomes, not the processes. To explore these possibilities, some scientists use computational models to simulate how early ecosystems behave under varying conditions. These models can show how small changes in nutrients, temperature, or light availability might lead to different community structures. They help researchers understand how ecosystems might reorganize during times of instability. While these models cannot reveal exactly what happened, they demonstrate how easily complex behavior can emerge and disappear without leaving fossils. In addition to modeling, researchers also examine preserved structures from periods older or younger than the gap. When they find examples of early multicellular forms, coordinated microbial networks, or unusual biological shapes, they consider whether similar forms might have existed earlier. If life experimented with these structures once, it might have done so multiple times. The missing interval could hold earlier attempts that did not survive. These attempts may have influenced the forms that eventually appear in the record after sedimentation resumes. The idea of civilizations that nearly were must be understood not as literal societies, but as biological systems approaching new forms of organisation. These systems could have shaped environments in coordinated ways. They may have spread across the seafloor or formed interconnected colonies capable of altering local chemistry. While not civilizations in any human sense, they represent steps toward complexity, each shaped by the challenges of their time. Some researchers also consider whether early life created structures that left faint, physical impressions later destroyed by erosion. For example, microbial communities can produce layered mounds or ridges in sediments. These structures can fossilize when conditions are right, but during the missing interval, conditions appear to have been unfavourable. Even if large microbial structures existed, they would have been vulnerable to removal. Their absence does not rule out their presence. It only reflects the instability of the environment. Still, the fascination with what might have existed stems from more than scientific curiosity. The missing interval forces a recognition that entire worlds of biological possibility can exist without leaving direct evidence. This recognition makes the period feel like a darkened room, where shape and movement are sensed without being seen. The room was not empty. It simply lacked the surfaces needed to hold impressions. From a scientific perspective, the importance lies not in imagining mythical civilizations, but in understanding that biological complexity often rises in forms that do not fossilize. The missing interval may have contained early steps towards structures that appear clearly only later. These steps, lost as they are, remind researchers that evolution is fundamentally experimental. One of the most puzzling features surrounding the missing interval is how evolution appears to behave differently on either side of it. When scientists compare the biological patterns before the gap to those emerging afterward, they notice a contrast that suggests something interrupted, redirected, or obscured evolutionary progress. The difficulty is determining whether evolution truly slowed or shifted during the interval, or whether the appearance of interruption is simply an illusion created by missing layers. Without the sediments that normally track incremental change, the fossil record jumps from one stage to another without showing the steps between them. That jump raises questions about whether the organisms of the time faced pressures that altered their evolutionary trajectories, whether populations dwindled in ways we cannot detect, or whether the entire seeming pause is the result of erasure rather than biological stasis. To make sense of this, researchers first consider how evolution typically leaves its mark. Under normal circumstances, gradual changes within ecosystems appear as slow transitions. Fossils diversify in shape, trace fossils become more complex. Chemical signatures show new metabolic pathways emerging. Even in periods where life remains simple, small adjustments become visible through careful study. But when an interval leaves no fossils, traces, or reliable sedimentary layers, these gradual adjustments vanish from the timeline entirely. The rock record before the gap may show moderate diversity, while the rock record after shows a new configuration, yet everything between appears blank. This blankness challenges scientists to determine whether evolution paused, or whether the record merely failed to preserve a period of significant change. One approach to this problem involves analysing the last known communities before the gap. These communities often show stable patterns, with organisms adapted to conditions that appear consistent for long spans of time. The chemical and mineral textures in the surrounding layers suggest ecosystems functioning in predictable ways. When these same kinds of features reappear in younger layers, they sometimes show clear differences. The shift does not look chaotic or abrupt. It looks like the outcome of slow processes unfolding over the gap's duration. This suggests that evolution likely continued even when the Earth stopped preserving evidence. Organisms probably responded to environmental changes, explored new niches, or developed new physiological traits. But the signatures of these developments disappeared with the missing pages. Another way researchers explore this issue is by examining how organisms in later periods appear relative to earlier ones. If evolutionary rates had slowed during the gap, we might expect post-gap organisms to closely resemble their ancestors, but in many cases differences do exist. They may be subtle, changes in metabolic strategies, new ecological roles, or slight variations in morphology, but they indicate ongoing evolution. The challenge lies in reconstructing the path that led from the earlier forms to the later ones. Without intermediate fossils, that path exists only as a conceptual bridge rather than a documented sequence. There is also the possibility that certain evolutionary pathways paused during the interval, not because life itself was stagnant, but because environmental pressures stabilized communities for long stretches. When conditions remain steady, organisms often maintain their existing traits rather than developing new ones. Evolution becomes more conservative. If parts of the missing interval experienced environmental constancy, this could explain reduced evidence of diversification. Yet even stable environments produce some degree of evolutionary experimentation. Subtle genetic variations accumulate over time, even if they do not manifest in ways that fossilize. The problem is that these slight changes, if not accompanied by structural modifications, leave no discernible geological evidence. Researchers also consider scenarios where evolution did not pause at all, but shifted direction. Environmental instability can push ecosystems into modes of adaptation that differ from those seen in more stable periods. For instance, if nutrient availability fluctuated, organisms might have developed strategies for resilience rather than diversification. If chemical gradients change frequently, metabolic flexibility might have been favoured over morphological innovation. These evolutionary responses may not produce fossilizable structures, but can still alter ecosystems dramatically. When stability later returns, the organisms that emerge in the sediment record may appear different, because their ancestors adapted to fluctuating conditions in ways we cannot detect directly. A more complex scenario involves the possibility that certain evolutionary experiments failed during the missing interval. Evolutionary history is filled with branches that never lead to dominant groups. Some organisms develop new forms or behaviours only to disappear when conditions shift. If such experiments occurred during the gap, they may have left no descendants and no fossils. Their absence in the record would make it appear as though evolution paused, when in reality it was active but ultimately unsuccessful in producing lasting lineages. The missing interval may have held numerous such attempts, each contributing to the shaping of ecosystems even if they vanished without leaving evidence. Chemical signatures surrounding the gap sometimes hint at biological changes not reflected in fossils. Shifts in carbon or sulfur isotopes can indicate changes in the relative abundance of certain types of organisms. These signatures may reflect new metabolic pathways emerging during the gap. If microbes with different chemical preferences rose to prominence, they would influence global biogeochemical cycles. These influences could appear in younger rocks even if the organisms themselves did not fossilize. Such chemical deviations provide indirect evidence of evolutionary activity, even if they cannot be tied to specific life forms. Another dimension of this problem involves extinction. Extinction does not always leave a clear boundary layer filled with fossils. Small-scale extinctions or prolonged declines can occur silently, especially in environments where fossilization is unlikely. If certain lineages dwindled during the gap, their disappearance might go unnoticed. Only when younger layers appear, showing a different set of organisms, do scientists realize that older communities did not persist. In such cases, it might appear as though organisms simply changed or evolved into new forms, when in fact entire groups vanished quietly, while others filled their ecological roles. One reason scientists tread carefully in interpreting evolutionary behaviour during the gap is that missing evidence frequently creates illusions. When intermediate layers vanish, the biological story can seem more abrupt than it was. A lineage that appears stable before the gap may seem to transform suddenly afterward, even if the transition was gradual. Conversely, the absence of transitional fossils may give the impression that evolution paused, when the truth is that the transitions occurred unseen. The missing sediment compresses long spans of evolutionary change into a single apparent leap. Recognizing this distortion requires careful interpretation of both biological patterns and geological context. Some researchers turn to evolutionary models to fill in these gaps conceptually. By simulating how organisms evolve under different environmental pressures, they can generate plausible scenarios for how life might have behaved during the interval. These models suggest that evolution rarely halts completely. Instead, it shifts pace depending on environmental conditions. Under stable conditions, change slows. Under unstable conditions, diversification may accelerate or follow non-linear paths. The missing interval may reflect a combination of these modes, creating patterns that appear inconsistent when viewed only through the layers that survived. To further complicate the issue, environments during the missing interval may have been fragmented. If continents were positioned in ways that created isolated habitats, evolution could have proceeded differently in separate regions. Some areas may have experienced population bottlenecks, others may have supported bursts of diversification. These processes could produce significant global change even if no fossils remained to document them. When sedimentation resumed, only the results would appear, giving the impression that change occurred suddenly across the whole planet, even if it actually unfolded unevenly. The potential for evolutionary pauses also requires considering the chemical environment of the time. For evolution to progress, organisms need access to nutrients and favourable conditions for survival. If nutrient cycles faltered during the interval, perhaps due to ocean stratification, shifts in circulation, or atmospheric changes, evolution might have slowed because organisms lacked ecological opportunities for diversification. A nutrient-limited world tends to favour simple, resilient organisms. New innovations may still arise, but they may not proliferate widely. The organisms that do persist leave little footprint in the record if sediments fail to bury them. On the other hand, shifts in ocean chemistry could have opened new ecological niches. If oxygen concentrations or trace metal availability changed, organisms may have adapted in ways that later allowed more complex life to emerge. These adaptations might not leave fossils during the gap, but they could influence the traits seen in organisms afterward. This makes the gap a potential turning point even if the turning point itself is invisible. Another possibility is that environmental pressures forced certain lineages to reduce in size or metabolic complexity temporarily. In harsh conditions, organisms often shrink, simplify, or retreat into minimal forms of existence. These small or simplified organisms rarely fossilize. If evolution took this path during the gap, it would look like a pause in complexity even though adaptation continued. Only after conditions improved would more complex traits reappear. The record after the gap may reflect this resurgence. Researchers also explore whether genetic evolution might have occurred without structural expression. Genetic changes can accumulate silently for long periods, becoming relevant only when triggered by specific conditions. If such changes built up during the gap, the organisms emerging afterward may appear to evolve rapidly. This apparent burst could be the result of genetic groundwork laid during the missing interval. The absence of fossils masks the long preparation, making the post-gap diversification seem sudden. Although direct evidence remains lost, scientists continue to find small hints at the edges of the gap. In some regions, microscopic structures appear just before sedimentation resumes. These structures may reflect early stages of organisms adapting to new conditions. Even though they are incomplete, they give glimpses of shifts underway. These glimpses suggest that evolution was not idle. It worked quietly, shaped by conditions that did not favour preservation. Taken together, these possibilities show that the question of whether evolution paused is more complicated than it appears. Evolution does not depend on fossilization. It occurs regardless of whether sedimentary layers survive. The absence of evidence during the gap does not reveal what did or did not happen biologically. It only reveals how much the geological processes of the time failed to capture. The subtlety of these ideas becomes clearer as researchers study later periods, where similar gaps occur on smaller scales. In many such cases, evolution seems to leap from one stage to another only because intermediate layers are missing. When those layers are found elsewhere, the gradual nature of change becomes obvious. The missing interval we're exploring likely masks similar continuity. The apparent pause, shift, or disappearance is therefore a product of geology rather than biology. What emerges from this perspective is not a story of stopped evolution, but one of unseen transitions. These transitions influenced everything that came later, shaping organisms in ways the rocks only hint at. Conditions during the missing interval appear to have shaped the world in ways that pushed life toward places where the record seldom survives. Instead of expanding across broad environments that typically preserve fossils well, organisms may have retreated into narrow ecological pockets where stability still existed. These pockets often occupy the margins, areas along coastlines, around hydrothermal systems, within sheltered basins, or in microenvironments that resist large-scale disturbance. Life has always taken refuge in these kinds of marginal settings during difficult periods. When climates shift or sedimentation breaks down, the organisms unable to thrive across wide spaces tend to cluster where resources remain sufficient. If a similar pattern unfolded during the missing interval, it would help explain why the fossil record goes silent, even though biological activity almost certainly persisted. To understand why this matters, it helps to consider how marginal environments function. These places are often small and patchy, with conditions that vary over short distances. They may be shielded from strong currents, protected from erosion, or isolated from broader environmental changes. Microbial mats flourish in such areas, forming stable layers that develop over long periods. Hydrothermal vents provide chemical energy independent of sunlight, supporting communities that survive even when surface conditions deteriorate. Shallow pools trapped between tides can harbour organisms adapted to fluctuating salinity and temperature. These settings offer refuge during times when the wider environment becomes inhospitable. But although marginal spaces support life effectively, they rarely preserve it. Fossilization requires rapid burial or the presence of minerals that stabilize organic matter. Many marginal environments lack such conditions. Microbial mats, for example, often erode before they can be buried. Hydrothermal vent communities inhabit regions where geological processes frequently disturb sediments. Tidal pools fluctuate too much to allow continuous deposition. Even when burial occurs, chemical conditions in these environments may dissolve organic material before it fossilizes. So while life thrives in these pockets, the chances of leaving a durable record remain slim. If much of Earth's life during the missing interval existed in these kinds of habitats, the disappearance of fossils becomes less mysterious. Evolution, adaptation, and ecological interactions could have continued actively, but the environments where they unfolded would have been poor at preserving any evidence. The main sedimentary basins, which usually capture the broad story of life, were likely unstable. Erosion may have dominated, or deposition may have been too slow. Meanwhile, the places where life persisted offered the stability needed for survival, but not the stability needed for fossilization. As a result, life's story during the gap became confined to environments that did not participate in sedimentary record-keeping. One area of interest is shallow coastal zones. These regions often act as transition spaces between land and sea. If sea levels fluctuated during the missing interval, coastal environments may have expanded, contracted, or shifted constantly. Organisms adapted to these settings might have followed the retreating or advancing shorelines, staying within regions that offered favourable conditions. Such mobility helps life survive but makes preservation less likely. When coastlines migrate, sediments that form in one position may be reworked when water levels change. The constant movement smears the geological record, erasing any traces left behind. Another marginal environment worth examining is the deep ocean, particularly the areas around hydrothermal vents. These vents provide energy-rich environments capable of supporting diverse microbial communities. If surface conditions became unreliable during the missing interval, the deep ocean may have offered a relatively stable refuge. But deep-sea preservation is rare. Sediments accumulate slowly, and vents often produce unstable geological conditions that disrupt deposition. Even when remains are buried, the chemistry of vent systems can dissolve organic matter. Life in these environments may have been vibrant yet entirely unrecorded. Wetlands and estuaries present another possibility. These environments form in places where rivers meet seas, creating nutrient-rich zones that support robust microbial and early multicellular communities. During periods of environmental stress, wetlands often serve as refuges because they buffer temperature changes and provide consistent moisture, but their sediments frequently degrade organic matter before it fossilizes. Wetlands can also shift position when sea levels change, removing deposits that might otherwise record biological activity. If life concentrated in such settings during the missing interval, its absence in the fossil record would be expected. Even soils may have hosted important communities during the gap. Primitive soil crusts formed by microbial colonies can stabilize surfaces and influence erosion. These crusts act as biological communities in their own right, shaping local chemistry and interacting with their surroundings. But early soils almost never fossilize. Soil formation relies on processes that mix organic and mineral components in ways that hinder preservation. Erosion easily removes them. If early terrestrial or near-terrestrial life existed in these soil-like surfaces, it would leave little trace. Beyond physical settings, marginal environments offer another insight. They often support organisms uniquely adapted to extreme or fluctuating conditions. These organisms tend to be resilient, flexible, and capable of surviving across a broad range of circumstances. When environmental pressures increase, such organisms often become more widespread. If the missing interval involved instability in climate, sea level, or chemical conditions, marginal adapted organisms may have dominated. Many of these forms are small, soft-bodied, or structurally delicate, making them unlikely to fossilize even under favourable conditions. Their dominance would further limit the likelihood of preserved remains. One key idea researchers consider is that life may have retreated not only into marginal spaces geographically, but into marginal metabolic niches as well. When conditions become difficult, organisms sometimes shift to survival strategies that involve slower growth, reduced metabolic activity, or the use of alternative energy sources. These strategies help populations persist through stress, but do not encourage diversification or morphological innovation. As a result, evolutionary changes during such periods may be subtle and invisible in the fossil record. These shifts can still influence future evolution, but they leave little direct geological trace. Chemical evidence supports this idea. In layers before and after the gap, certain isotopic patterns suggest that oxygen, carbon, or sulfur cycles may have shifted. These shifts could result from changes in which microbial groups dominated. If organisms relied more heavily on anaerobic metabolism or alternative chemical pathways, their activity would influence global biogeochemistry without producing fossils. These signals may appear faintly after the gap because they reflect long-lasting trends rather than sudden events. There is also the possibility that marginal environments acted as reservoirs for genetic variation during the missing interval. Populations under stress often accumulate genetic diversity quietly. This diversity may remain hidden until conditions improve. When environments stabilize, populations that survived in refuge zones can expand suddenly. The organisms emerging in younger rock layers may therefore seem more diverse or more complex than those in older layers, even though the changes occurred gradually within the unseen interval. This gives the illusion of rapid post-gap evolution when, in reality, the groundwork was laid earlier. Researchers studying similar patterns in later periods note that life frequently persists in small scattered refuges during environmental disruptions. For instance, during ice ages, Some species survive in pockets of favourable climate called refugia. After the ice retreats, these species repopulate broader regions. Their sudden appearance in more widespread environments can seem abrupt in the geological record, even though they survive the difficult period continuously. If a similar process occurred during the missing interval, but on a far more ancient and global scale, it would explain the abrupt appearance of new communities afterward. To test these ideas, scientists study environments today where conditions resemble early Earth. Microbial mats in tidal flats, extreme desert crusts, deep ocean vents, and subglacial lakes all offer analogues for marginal habitats. These modern environments host abundant life, but leave minimal lasting traces. When sediments form, they often preserve only indirect indicators such as chemical gradients or mineral structures. This reinforces the idea that the missing interval could have hosted extensive biological activity without leaving fossils. The parallels, while imperfect, help researchers imagine how early life might have persisted through instability. Another dimension of the marginal life hypothesis involves the availability of ecological space. If broader ecosystems declined during the gap, whether through erosion, altered chemistry, or changing sea levels, margins may have become the only viable habitats. This concentration of life into pockets reduces the likelihood of widespread fossilization. It also creates opportunities for unique adaptations that do not spread widely enough to appear in later fossil records. The communities that emerge after the gap may reflect the traits of organisms that survived at the margins rather than those that once thrived more broadly. Additionally, marginal habitats often serve as zones of environmental mixing. Chemical gradients, fluctuating conditions, and shifting resources create opportunities for novelty. Microbial communities in such settings can reorganize frequently, developing new metabolic capabilities or cooperative behaviors. These innovations can shape evolution even if they remain confined to small spaces. The absence of the record during the gap prevents us from seeing these experiments unfold, but the post-gap biological landscape may bear their influences. One of the more intriguing implications of this idea is that the missing interval might represent a time when life diversified in ways that do not fossilize. Soft-bodied organisms could have explored early versions of multicellularity, coordination, or symbiosis. These forms may have been short-lived or confined to small habitats. Their disappearance from the rock record would be expected if erosion dominated or if chemical conditions prevented their preservation. But their existence could have shaped the evolutionary possibilities available later. Even today, much of Earth's biomass resides in environments that rarely fossilize: deep subsurface microbes, hydrothermal vent communities, and soil microorganisms. These organisms drive key processes but leave almost no geological record. If similar groups dominated during the missing interval, their absence in the rock record reflects not their insignificance but their invisibility, a recurring theme in the early history of life. When sedimentation resumed after the gap, the organisms that had survived in marginal settings spread into new habitats. Their expansion may have created the appearance of sudden ecological change, but if these organisms had been evolving quietly in isolated pockets, the reappearance of the sediment record simply reveals their next stage, not their origin. The idea that life hid in the margins underscores how survival often depends on finding stability where little exists. The missing interval may have been a time when the world offered stability only in small scattered places. Everything outside those places shifted faster than the processes that preserve history. Everything inside them endured without leaving durable signs. Understanding why so much of Earth's past remains hidden begins with recognizing that the planet is not designed to preserve its own history. It changes too quickly, too often, and too completely for most details to remain intact. The rocks that do survive represent only a thin portion of what once existed. Everything else has been folded, eroded, dissolved, buried too deeply, or never recorded at all. The missing interval we've been following is only one instance of this larger pattern. Throughout Earth's timeline, there are stretches where the planet behaved in ways that prevented memory from forming. These stretches remind us that forgetting is not accidental. It is a natural outcome of how Earth works. Geologists often describe the planet as restless, and that restlessness shapes what survives. Mountains rise and crumble. Basins open and fill, only to empty again. Seas advance and retreat, creating new surfaces and removing old ones. Even the continents drift, slowly rearranging the environments where sediments might accumulate. All these movements disrupt the process of preservation. If conditions fail to align long enough for layers to form and harden into stone, whatever happened during that time disappears. The Earth does not erase its history intentionally, but its normal behaviour ensures that only a fraction of events are recorded. Preservation itself demands precision. A layer must form in a place where sediments collect faster than they erode. Organic material must be buried rapidly. Chemical conditions must favour mineralisation rather than decay. Pressures and temperatures must remain within ranges that allow the material to survive long enough to become rock. After that, it must escape being broken, bent, melted, or dissolved as millions of years pass. These requirements create a narrow window through which only certain environments and organisms can leave durable traces. Life and landscapes that fall outside this window vanish almost automatically. This helps explain why Earth's record contains so many gaps, both small and immense. The missing interval is striking not because it is unusual, but because its scale and consistency make it stand out. Smaller gaps exist throughout the rock record. Some span thousands of years, others millions. Each one represents a time when conditions prevented preservation. Sometimes erosion removed layers that once existed. Sometimes deposition slowed or stopped entirely. Sometimes rocks that formed were altered beyond recognition. These interruptions are part of how geology works, not exceptions to it. One of the reasons the planet keeps secrets so effectively is that the forces shaping it work continuously. Erosion alone can remove vast amounts of material silently. Rivers cut through rock, carrying sediment far from its origin. Wind and water abrade surfaces. Ice grinds down mountains. As soon as a layer forms, the process of removing it begins. Over long spans of time, even resistant rocks succumb to these forces. The longer the interval, the more opportunities erosion has to reshape or eliminate it. Tectonic activity contributes further to this loss. When continents collide, rocks fold and compress, transforming their minerals. When they separate, the crust thins and stretches, exposing deeper layers to the surface. In both cases, the original structure of the rock record becomes distorted or erased. Heat and pressure within the crust can change minerals so thoroughly that any fossils or sediments once present disappear entirely. What began as a clear record of an ancient environment may become nothing more than metamorphic rock, with no remaining signs of its origin. Chemical alteration adds yet another layer of erasure. Water circulates through rocks, dissolving minerals and precipitating new ones. Over time, these interactions can obliterate subtle details. Organic material that might have preserved traces of early life may degrade or transform beyond recognition. Even isotopic signatures, which often survive when fossils do not, can be modified by later processes. Without those chemical markers, the task of reconstructing ancient conditions becomes more difficult. Because so many processes destroy or obscure the past, the layers that remain must be interpreted with care. They represent the survivors of countless cycles of change. Scholars often compare the geological record to a library in which entire shelves have vanished, leaving only scattered volumes. From those volumes, one must infer the contents of all the missing ones. The missing interval we're following is one such empty shelf. Its absence challenges scientists to determine what kinds of books once filled that space. The Earth's tendency to hide its past becomes even clearer when we consider how rarely environments form the kinds of sediments that preserve fine detail. Most of Earth's surface is either erosional, where material is removed, or depositional in ways that do not capture biological remains. Deep oceans, deserts, mountains, and riverbanks all interact with sediments in ways that make preservation unlikely. Only certain settings, calm lakes, shallow seas, river deltas under specific conditions, allow fossils to form consistently. Even within these settings, the window for fossilization opens only occasionally. This inconsistency means that the fossil record is not a complete timeline, but a series of snapshots. Between each snapshot lies a span of time where conditions may have prevented recording, or where later processes destroyed what was recorded. The missing interval represents a long gap between snapshots. The rocks before and after it show different patterns, but the transition between them is lost. Because the Earth keeps secrets so easily, scientists must use indirect clues to fill in missing information. Chemical signatures provide one set of clues. Patterns in isotopes, minerals, or organic molecules reveal how environments may have changed. They indicate whether oxygen increased or decreased, whether ocean chemistry shifted, or whether certain biological processes dominated. But even these clues can be incomplete or ambiguous. Similar patterns can arise from different causes. Without the rocks from the missing interval, it becomes difficult to determine which scenario fits best. Another method involves looking at places where the gap is smaller. In some regions, the missing layers are thin or only partially eroded. These rare pockets hold fragments of information that escape destruction. They may show hints of environmental transition or signs of biological activity. These fragments do not offer a full picture, but they reduce the range of possible interpretations. By comparing them across different locations, scientists can build a broader understanding of what might have occurred globally. Still, the broader question remains: why does Earth allow some intervals to remain well preserved, while others disappear entirely? Part of the answer lies in environmental stability. When conditions remain consistent for long enough, sediments can accumulate steadily. Such periods often produce detailed fossil records. But when conditions fluctuate through climate shifts, tectonic movement, or changes in ocean circulation, preservation becomes erratic. The missing interval likely coincided with a time when Earth systems were out of sync with the requirements for record making. This mismatch does not imply catastrophe, it implies misalignment. Biological and geological processes did not align in ways that favoured preservation. Life continued, landscapes evolved, but the record-keeping mechanism faltered. Understanding this misalignment helps explain why entire spans of time can vanish, while others remain intact. Another reason the Earth keeps secrets is that its scale allows processes to act differently in different regions. One part of a continent might have been eroding while another accumulated sediment. One ocean basin might have been stable while another shifted. If the regions capable of preserving information were affected more strongly by erosion than by deposition during the gap, the global record would reflect absence rather than presence. Only by examining multiple locations can scientists identify patterns that hint at what might have occurred. Even when the geological record is absent, biological evolution continues regardless. The Earth does not pause because its memory stops recording. Organisms persist, adapt, and change in response to their environments. When the record resumes, new forms may appear or older ones may shift. These changes reveal that time passed and events unfolded even if the details are missing. The Earth keeps secrets not by preventing events, but by preventing their preservation. The endurance of these secrets also reflects the timescales involved. Over hundreds of millions of years, even well-preserved layers face threats. As continents drift, rocks containing fossils may sink beneath ocean basins or rise into mountains where erosion accelerates. Volcanic activity may bury layers deeply, where heat and pressure erase delicate structures. Without active human discovery, preserved layers might remain hidden indefinitely. Their absence in our knowledge does not imply absence in reality. This brings us to another important aspect of the Earth's secrecy, the limitations of human access. Much of the planet's crust lies beneath oceans, glaciers, dense forests, or thick layers of sediment. Many areas remain unexplored. Some preserved intervals may exist in places unreachable or undiscovered. The missing interval may not be missing everywhere, only in the places we have studied. New discoveries in remote regions could change our understanding significantly. Until those discoveries are made, many secrets remain beyond reach, not because they were erased, but because they lie hidden. Even in regions where rocks are accessible, their interpretation requires tools that are still evolving. Advances in imaging, chemical analysis, and drilling allow researchers to uncover details invisible decades ago. As these tools improve, previously indecipherable rocks reveal new information. What appears as a blank page today may eventually show faint writing. The Earth hides its secrets well, but not perfectly. With each technological advancement, the potential for uncovering fragments of the missing story increases. A deeper philosophical angle also emerges from this pattern. The Earth is not a storyteller by design. It records only what conditions allow. Much of what happens on its surface leaves no trace. Human attempts to reconstruct the past depend on what remains, not on what originally existed. The missing interval teaches that our knowledge of the past is fundamentally incomplete and always will be. No matter how detailed the record becomes, large sections will remain unwritten. This incompleteness is not a failure, but a feature of the planet's nature. The Earth is dynamic. It renews itself constantly. Old surfaces disappear as new ones form. Layered histories accumulate unevenly. The missing interval highlights how the processes that sustain life and shape landscapes can also erase their traces. In this sense, the Earth keeps secrets simply because it is alive with motion. The quiet that follows long stretches of uncertainty has a way of settling differently than the silence within the missing interval itself. When we look back over everything that remains unknown, the mind doesn't arrive at the sharp edges of frustration. Instead, it drifts into a gentler space where the limits of knowledge become part of the experience. The Earth has always offered more questions than answers, and the gap we've spent this time exploring simply highlights the natural boundaries of what can be known. These boundaries aren't walls, they are the places where imagination meets evidence, where patience meets unanswered patterns, where the world chooses not to reveal every moment of its past. In that space, one can pause without needing resolution, knowing that the mystery itself is a stable place to rest. This sense of ease comes partly from recognizing that the planet's silence is not hostile, it's structural. Rocks are not written with intention. Fossils do not arrange themselves for clarity. Chemical signals do not align themselves neatly for our analysis. The Earth produces patches of memory only when circumstances line up in ways that allow them to survive. Those circumstances are rare, delicate, and often temporary. When they fail, the past slips away cleanly. The missing interval is simply an example of that slipping, and instead of resisting its emptiness, the mind can settle into its scale, appreciating how vast stretches of time passed without leaving marks strong enough to outlast the planet's restless surface. There is a certain calm in acknowledging that not every moment of Earth's history was meant to be reconstructed. The world existed well before humans developed the tools to examine it. The processes that erased the gap began long before those tools were imagined. The planet moved through cycles of erosion, deposition, uplift, and weathering without concern for future interpretation. Life adapted, responded, shifted, and endured through landscapes that changed too quickly or too subtly for preservation. These truths complicate our efforts to build a complete timeline, but they also relieve us from expecting perfection in the record. What we have is enough to understand broad patterns, even if fine details remain hidden. And what we don't have becomes part of the deeper rhythm of Earth's story. When we step back and picture the world during the missing interval, we may feel tempted to fill the silence with explanations that match the scale of the gap. Large absences invite large ideas, yet, as we've explored, The most plausible scenarios involve processes that unfold quietly rather than catastrophically. Erosion that works slowly, removing layer after layer, sea levels shifting just enough to prevent stable sedimentation, microbial communities adapting in ways that produce little physical trace, climate fluctuations that nudge ecosystems from one configuration to another without leaving thick deposits. Each of these influences can last millions of years, reshaping the planet without leaving behind dramatic signatures. When framed this way, the missing interval becomes less like a lost chapter and more like a period when the Earth was simply living through conditions that did not lend themselves to memory. There is reassurance in that perspective. It means the gap is not a void to fear, but a reminder that change does not always leave a record. Much of our own experience works similarly. Not every day becomes a story. Not every moment lodges in memory. Some stretches slip by quietly, shaping us in ways we notice only later. Earth's history moves in the same manner. The missing interval shaped what came after it, even if it didn't preserve how. The later layers show reorganized environments, renewed sedimentation, and different biological patterns, all of which imply that the unseen period carried momentum into the eras that followed. The influence is real, even if the details remain inaccessible. Thinking about this influence brings the mind to a softer place. The uncertainty becomes less a problem and more an invitation to consider how much of life, past or present, happens outside the frame of what can be recorded. Entire lineages rose and vanished during the missing interval. They left no fossils, no traceable structures, no clear chemical signatures, yet they formed part of the continuous flow of evolution. The world did not pause. Ecosystems did not stop functioning. The absence in the rocks simply reflects the absence of the conditions needed to preserve their presence. Knowing that life continued across that silence adds a sense of continuity that balances the emptiness. The story didn't stop. Only its documentation did. This continuity extends beyond biology. Landscapes shifted in response to forces that work at scales too large for human intuition. Mountain ranges rose gradually. Rivers carved their paths with unhurried persistence. Sea basins deepened or filled, directing the movement of ancient currents. All of these changes might have influenced why the gap formed and why the record disappeared. Even though we cannot see the exact details, we can understand the processes well enough to imagine their presence. The Earth kept moving, adjusting and reshaping itself just as it always has. The missing interval is an expression of that motion. Accepting the mystery also creates space to appreciate the moments when the planet chooses to preserve things. The fossil beds, mineral signatures and layered rock formations that do survive represent rare alignments. They form only when environmental and geological conditions cooperate precisely. These preserved moments appear sporadically through time, providing glimpses into ancient worlds. For every glimpse, there are countless moments lost. Instead of feeling incomplete because of what is missing, one can feel fortunate for what managed to survive. The missing interval helps recalibrate that sense of proportion. It emphasizes that geological preservation is the exception, not the norm. Reflecting on the exceptionality of preservation shifts the focus toward gratitude rather than frustration. The rocks before and after the gap tell stories that stretch across unimaginable spans of time. They contain subtle patterns that scientists can read with increasing precision. They reveal how life adapted, how environments changed, how continents moved. These surviving details create a framework that guides our understanding of the planet's deep past. The missing interval fits comfortably within this framework, not as a failure of information, but as a reminder of the limits of even the most detailed archive. In this light, the mystery becomes a part of the planet's character. Earth has always been a place where knowledge comes in fragments. The earliest chapters of life remain faint. Many transitions are obscure. Entire ecosystems appear suddenly in the record because earlier sediments did not survive. The missing interval enlarges this pattern, but does not fundamentally change it. The planet has always kept some secrets, and it will continue to do so long after humans stop asking questions. What remains most striking is how much we can still infer despite these secrets. The chemistry of younger layers hints at environmental conditions that followed the gap. The disappearance of certain sedimentary structures implies what kinds of processes dominated. The appearance of new biological forms suggests evolutionary transitions that occurred out of sight. These indirect clues allow us to reconstruct broad outlines of what happened even if the specific details remain obscured. The missing interval challenges researchers to think creatively, test hypotheses patiently, and refine interpretations as new tools emerge. The process mirrors the nature of scientific inquiry itself, careful, incremental, and open to revision. This incremental approach brings a sense of calm when thinking about the unknown. The mind settles into the understanding that knowledge does not need to be complete to be meaningful. Each discovery adds clarity, but each unanswered question adds space for further exploration. The missing interval offers a balance of both. It contains just enough information at its edges to inspire inquiry, but enough absence in the middle to avoid closure. That balance invites reflection rather than frustration. The comfort found in reflection extends beyond the scientific details. There is something inherently soothing about acknowledging the enormity of geological time. The missing interval spans millions of years, years during which life persisted in ways we cannot fully imagine. Considering that scale shifts our perspective, daily concerns shrink. The pace of human life becomes only a thin layer atop a much older story. The silence of the gap becomes a reminder that the world has endured far more than what is preserved. It has weathered changes far greater than the absence of a few rock layers. That resilience adds a sense of stability to the uncertainty. Because the missing interval sits so far in the past, it also feels distant from urgency. It invites contemplation rather than urgency. It becomes a place in the imagination where the mind can drift, exploring possibilities without needing definitive conclusions. The calmness of that space aligns with the tone of these quiet reflections. Instead of analysing urgency, we acknowledge curiosity. Instead of demanding answers, we rest with open questions. The Earth's secrets, in this sense, are not barriers. They are open-ended invitations. Each unanswered question widens the range of what might be imagined. Scientists continue searching for clues, not because mysteries are inconvenient, but because they expand the scope of understanding. The missing interval extends that expansion by offering a long stretch of time where the story continues silently beneath the surface. As more discoveries emerge through careful study, some of the missing details may gradually come into focus. New techniques might reveal subtle chemical gradients. Undiscovered rock formations might contain faint traces that escape destruction. Yet even if some portions remain forever hidden, the presence of mystery does not diminish the rest of the story. It enriches it. The absence becomes part of the narrative, shaping how the rest of the evidence is interpreted. Resting with that uncertainty brings a gentle kind of closure. Not the closure of answers, but the closure of acceptance. The Earth kept its secrets not to confuse us, because the processes that shape it do not prioritize record keeping. The missing interval is a reminder that our understanding of the past coexists with the unknown. There is a quiet reassurance in acknowledging that coexistence, and now, with the landscape of unanswered questions settled softly in mind, the thoughts begin to ease. The world becomes quieter. The scale of time stretches comfortably in every direction. The details we know blend with the ones we don't, forming a steady backdrop where curiosity can pause without fading. The mystery remains gently intact, asking nothing more than to be considered for a moment and then allowed to rest.